So, hi, I'm Stuart, and I am going to talk about sharing. So, I was asked to talk about, speak on the topic of calculating quantities, and I wasn't really sure what to do with that. So you're all probably better coders than I am. I mean, that's my experience anyway. When students come into my group at Berkeley, they're all way ahead of me, right? They're all way ahead of me. So I can't really teach you much about Python or writing code or anything like that. So what I thought I'd do is try to motivate how to choose units and coordinate systems for your data analysis to be sort of physics appropriate rather than just subtle for what you get out of a data stream. And so, okay, but I thought before, and I asked Nick if I could do this, I thought I would introduce myself a little bit because when I was a student, I went to summer schools at, Tom Chang used to host these summer schools at MIT. I don't know if anyone remember those, Mark? Yeah. And I went to those things, and I think, the two things that I got out of them the most, the two things that I recall are meeting people as, kind of forming a cohort, kind of the sociology of it, meeting the people who will become your colleagues later. And then also talking to the tutors and the teachers and seeing kind of what their deal was, how they chose their problems, how they sculpted their careers, whatever. I knew I wanted to be a scientist. I wasn't sure exactly what I wanted to do. So I thought I'd tell you just a couple slides about who I am and why I'm here. Okay, so I was a student many years ago now. 1994, I finished my PhD at the University of Minnesota, and I worked on sounding rocket experiments. We had two experiments at the time that I worked on. One was called Electron Echo 7, and this was an experiment that went up to about, we fired a rocket up to about 1,000 kilometers or so, and it had an electron gun on it. It had a beam, an artificial beam that we fired along the magnetic field direction in a coded pulse. It was about, I think it was 35 keV or so, so it was a fairly high energy beam. And those electrons followed the Earth's magnetic field to the conjugate point at the South Pole, and they mirrored and they bounced back along the field line. And the pulse was designed, the coded pulse was designed to be long enough that we could identify individual bursts of the beam. And so we could measure by knowing the beam energy, we knew the speed of the beam, and by knowing the timing, the delay between the bursts, we could measure the field line length. So we measured the length of the magnetic field line, and we could also see drifts associated with electric fields. So this was a really cool experiment, and it was really successful, and it motivated us to do another experiment that we called SKEX3, several compatible experiments. And the idea of this experiment was to bounce an electron beam off of the Earth's auroral region. So the auroral potential drop is in the order of a kilovolt or something like that. So we thought, well, if we fire a beam that's lower energy, maybe a couple hundred volts, up into the auroral acceleration region, we could bounce it back and measure it back on the rocket. But at those low energies, you had to have a very dense beam because there's more thermal plasma there. And so we injected a very dense beam into the plasma, and it made our rocket charge up like crazy. And it made a giant discharge around the rocket. And so it was a big failure. And so, I mean, there was a lot of plasma physics, but the experiment as we designed it failed. So that was my first failure. That was actually my thesis project. And then when I finished up, I was finishing up in 1994, and it was the year that the comet Shoemaker-Levy 9 impacted Jupiter. I don't know if you'll remember that. It was a comet that had a close encounter with Jupiter, tidally broke it up into, I think, 19 separate pieces, went around the sun again, and it came back towards Jupiter, aimed right at Jupiter. And so the predictions were that it was going to hit. And we had this idea that as the pieces of the comet went through the Jovian magnetosphere, they would radiate in the same way that Io, the Jovian moon, radiates as it goes around the planet. It has a kind of a unipolar generator that generates decametric radio emission, 10 to 40 megahertz or so. So we had this idea, and we convinced the dean at the University of Minnesota to give us $100,000 to build an experiment and take it to a place where we could make these measurements. And the place turned out to be South Africa, which was in opposition for 11 of the impacts onto Jupiter. And it was winter in South Africa, so the ionosphere was thinner, a couple megahertz or so. And so we built these giant log periodic antennas that turned out to be too big to move almost, with pulleys and ropes and that sort of thing. And we steered them across the sky at night by hand, trying to follow Jupiter, keeping Jupiter in the beam and making measurements. And we got nothing. I mean, it worked. We could see the sun, we could see the Jovian decametric emission, but we couldn't see anything associated with the Shoemaker-Levy 9 impacts. And so when you see a paper that has the word limits in the title, you know that it's describing a null result. Okay, but it was fun. It was a blast. It was like 6 weeks in South Africa just after apartheid. It was a really exciting, interesting place. Okay, then on to the next failure. I went to Queen Mary College in London to be a postdoc in 1994 with Steve Schwartz and David Burgess. Maybe some of you know Steve was here at last for many years. And I was hired to work on a mission, a European Space Agency mission called Cluster, which was one of the first big, was the flagship multi-spacecraft mission. And I worked for 2 years developing software, analysis software in support of it. And then this is what happened to it when it went on the launch pad. It blew up, or it was blown up by the ionospheres people. And so that went into the ocean. But meanwhile, I had been working on calibrations for the WIND spacecraft, which was built in the lab at Minnesota. Part of it was, the instrument was built in the lab at Minnesota as a student. And so I just reverted to that and moved to Berkeley. And I've been there ever since. So I've been at Berkeley since 1997, first in a research position and then in a teaching position. And now I'm over all these failures in my life, my career. So perseverance. Okay, so let's talk about choosing units and coordinate systems. So like I said, I can't really probably compete with you in terms of coding and that sort of thing, and data access. You'll all be more sophisticated than I am. But I have over the years developed some ideas about what to do with data once you've got it in your hands. In particular, how to choose, or at least I want to motivate you to try to choose data products that make data products that are physics-based rather than engineering-based. There's so much more insight that comes from crafting a data product with a physics problem in mind. And the same is true of coordinate systems. Okay, so to motivate that, I want to show you a picture of, this is an instrument that we have on the Parker Solar Probe spacecraft, which you've maybe heard of. It's orbiting the sun, going in fact, later this year, we'll be into 11.4 some solar radii near the sun. So, okay, so what we use when we analyze do this science is we use measurements, right? So if someone tells you, the magnetic field at 1 AU is 10 nanotesla or something like that, what they really mean is the measurement of the magnetic field is 10 nanotesla, right? Because it's not really the magnetic field, it's a measurement. So to make an example here, right, if we have an electric field, this is supposed to be an electric field oscillating back and forth. It drives currents on these antennas. These are electric antennas. They're just pieces of conducting metal. So the electric field generates a current in the antenna. And then we sample that current with some, let's say, some transistor or something like that, some kind of amplifier. And there are all kinds of things we do to it, right? We have capacitors and resistors, and they modify the signal. Some of them are things that we know, we measure in the lab. Some of them are things we don't know. Then the antenna is sitting in the plasma. There's an impedance to the plasma around it. We don't know what that is. We can guess, but we don't know. And what comes out of all this analog electronics is another voltage, right? So this is not the voltage that went onto the antenna, but it's a different voltage, and it's been modified in sometimes mysterious ways by the signal path between the input and the output. Okay, then we take that voltage and we put it into a bunch of electronics. Okay, so we take that voltage that we took off, let's say this is that antenna, and we put it into a box, and we mess with it even more. And then eventually we chop it up and digitize it and make numbers out of it, right? And so those numbers come with clock pulses on them. There's a clock that's saying, make a number now, make a number now, make a number now. And you get the number and you get the time that it was made. And so this is just all numerical stuff. And this comes down to the ground from deep space. And it's mostly preserved, what was made on the spacecraft. The numbers that were made on the spacecraft are generally the numbers we get on the ground. But then we have to turn them back into science, right? So then there's a whole process to try to invert all of this stuff in software, right? And that's imperfect, right? And so what comes out the other end, the thing that we call the electric field or the magnetic field or whatever, isn't really the electric field or the magnetic field. It's something that's had all kinds of fingerprints put all over it by the machinery in between, and some by nature too. Okay, so the point is, when we do this, when we build this stuff, we need to talk to other scientists or engineers and tell them what we're doing, what we expect, et cetera. So we say, for example, that the voltage that comes out of this amplifier and goes into this port on this board will be between 0 volts and 10 volts. So we have to have a number. We have to have a way to talk to each other about this. And so we use what I call engineering units. And this is just a bunch of junk that I copied from Wikipedia. But, you know, we talk about volts, we talk about ohms, we talk about meters and kilograms and seconds and that sort of thing. And that's just the way that we exchange information. Like I said here, this is exchanging information between humans about human-made stuff, right? And nature doesn't know anything about, or knows very little about these things, right? You know, the sun is 696,000 kilometers approximately in radius, but the sun doesn't know what a kilometer is. The solar wind is, you know, 1,000 kilometers per second at its highest speed, but it does not. Kilometers don't mean anything to the plasma and the solar wind. Seconds don't mean anything. They mean something to us. That's how we can exchange information about them, but they don't mean anything to the system itself. And so this is just to motivate you to think of better units when you're choosing problems. Try to work in physics-based units. And have any of you, all of you, had a plasma physics course? Yeah. Okay. Good. So most of what we do, at least what I do in, you know, I'm kind of a solar wind person at the moment, but solar wind physics, magnetospheric physics, ionospheric physics is primarily plasma physics, sometimes collisional, sometimes collisionless, usually not, in our case, relativistic or anything like that. It's pretty simple plasma physics. And so I've found that working in units associated with plasma physics has been very helpful. So I think that, so here are some sample units that you might know about, of course. There are some characteristic timescales in a plasma, right? There's the cyclotron frequency, which is the period of gyration of a particle due to the Lorentz force around the magnetic field. There's the plasma frequency, which is the timescale of inertial motion of, let's say, electrons with respect to ions. Electrons are light, ions are heavy. There's some differential motion that's inertial. There's a collision frequency, which is the typical frequency or the typical rate of binary particle collisions, of Coulomb collisions. So it's the time between individual collisions. This one you have to be very careful with because it's got several approximations baked into it. In terms of speeds, the sound speed, which is quite obvious. We all know about the sound speed. The thermal speed, which is really just a measure of the random energy of the particles, right? It's the width of a distribution in some sense. In this case, a Maxwellian distribution. And the Alfvén speed, which is, of course, the speed of a magnetic field perturbation, a simple transverse magnetic field perturbation on a magnetic field line. Okay, so there's some nice frequencies, some nice speeds, and there are lengths too. There's a Debye length, which is the, you know, sort of the smallest natural scale in a non-relativistic plasma. Well, let's just say plasma, non-relativistic plasma. There's a collisional mean free path, which is the typical distance between Coulomb collisions. The inertial lengths, which are the typical fluctuation scale size of the inertial motion, and the gyro radius, which is the scale of the gyro motion. And then there are dimensionless quantities too, like plasma beta. Plasma beta is, of course, the ratio of the thermal pressure, which causes expansion in a gas, right? There's a gradient force that causes expansion, and the magnetic field energy density, which can either confine or exclude the plasma, depending on how big this value is. And from these things, you can create other dimensionless, or you can create dimensionless quantities. For example, Mach numbers, which are the ratio of a system speed, for example, the solar wind speed to an Alfvén speed or a sound speed. You can create dimensionless scales like the Knudsen number, which is a measure of the scale size associated versus a collisional mean free path. So these are the things. These are the ways you should frame your problems when you're working on collisionless plasma physics. Okay, so now I have a few examples. So what I'm going to do is basically go through some of my favorite examples, and some of these are things from my own work, and that's not to say that they're better than other things. It's just that they're the things that are easiest for me to talk about. Okay, so the solar wind. So we know that the solar wind is what we would call bimodal. The speed is bimodal, right? There's a there's what we call fast solar wind, and fast solar wind is typically 500 to 1,000 kilometers per second or so at 1 AU. The thermal energies on the order of 10 to 20 EV, maybe 5 to 20 EV for the electrons. The density is 1 to 10 per cc at 1 AU, and the magnetic field is around 5 nanotesla at 1 AU, and it fluctuates a lot. The magnetic field has a lot of alphanic fluctuations in it. And then at 1 AU, we also see what we call slow wind, which is slower, right? So in kilometers per second, it has a lower speed. It tends to be more dense, and it has fewer fluctuations in it. It tends to be more steady in some sense, or alphanic fluctuations, I should say. So there are some really nice measurements from the Ulysses spacecraft. This is from a paper by Dave McComas showing at solar minimum. So Ulysses was a European mission that went over the poles of the sun. And so what Dave has done here is plotted the speed of the solar wind as a radial variable, as a function of a latitude angle. And so this is over the north pole of the sun, and you see this very steady high-speed wind. And it's actually colored here for the magnetic polarity. So this shows that the magnetic field is outward in this region. So the field is outward and the wind is very steady. And then as you go through the ecliptic plane, the wind speed drops and becomes much more irregular until it comes out the south side, and then you have negative polarity field and again steady wind. So you can kind of imagine a dipole field, right, that goes around like that. It's not, of course, that's oversimplified because there's a current sheet in the center with a very steady fast wind. So, and we also know that at solar minimum, over the poles of the sun are large coronal holes. So these are big regions of open magnetic field, where the magnetic field goes from the solar surface out into the heliosphere without a lot of large closed loops or anything, just open structure. And so we like to say that the fast wind emerges from coronal hole structures. The slow wind, we're not quite so sure. It could come from the streamer belt. It may be, well, it's associated with the streamer belt. It's not exactly clear right now what the source is. And this all changes as you go to solar maximum. So at solar maximum, when the sun is at its most active, this is from the second orbit of Ulysses, you see that there is still high-speed wind over the poles, but there's a lot more structure, and there's more high-speed wind in the ecliptic plane too. So, okay, so we like to think of the solar wind as being bimodal, having these two states. Yes? The streamer belt, okay, the streamer belt is basically the solar wind in the ecliptic plane, at least let's think about solar minimum, where it's very, very simple, in the ecliptic plane. And so this is characterized by what we call helmet streamers. So these are these big structures that extend out into space in the white light. And it's where the heliospheric current sheet forms. So this outward radial field extends out into the heliosphere, and then there's inward field below. And so at some interface here, the fields have to be oppositely directed, right? So there's a large current there that we call the heliospheric current sheet, and it's very unstable. And below that structure, you can find closed loops. Okay, so the fast wind or the coronal hole wind is associated with magnetic field that just opens right up into space. But in the ecliptic plane, or anywhere there's not a coronal hole, you can have closed magnetic field loops below. And I have a cartoon on this in a little bit. I'll elaborate a little bit on that. So active region plasma is different again. So active regions are regions with very intense magnetic field associated typically with sunspots and flares and that sort of thing. And the jury's a little bit out on active regions, what they do for solar wind plasma. I think, in fact, we have some nice results from Parker Solar Probe recently. We think that we see distinct solar wind emerging from active regions that's very magnetized, extraordinarily magnetized. Almost, the density is negligible. It's almost all magnetic field. So the fast wind is pretty clear. The slow wind and active region wind is still, I would say we're still trying to understand that. Okay, but for the purposes of this, I just wanted to make the point that we like to say that there's fast wind and there's slow wind. Okay, so this is a paper that Justin Casper led in 2017 that I especially like, which makes this point, I think, about choosing the right variables. So what's plotted here? So we know that these are proton distributions on the right from the Helios spacecraft. And we know that proton distributions in the solar wind are often anisotropic. So these are distribution functions. They're contours of distribution function in a velocity space. And the dotted lines that you see here, if I can get my cursor going again, the dotted lines like this are the magnetic field direction through that. So you can see that there's a kind of a plane of symmetry in these things, and the magnetic field organizes that plane of symmetry. And so this is the velocity distribution along the magnetic field. This is the velocity distribution perpendicular to the magnetic field. And the sort of width of those features represents the temperature, right? So if you think of a Maxwellian distribution function, the width of it is the temperature. So we have what we call a bimaxwellian. So there's a Maxwellian in the direction parallel to the field, and there's a Maxwellian in the direction perpendicular to the field. And the temperatures of those two things are different, right? And it can often be extremely different by a factor of 100 or so. So think of, the equation of state of water, right? I mean, it's like if you had a chunk of water and it was steam in this direction, and it was ice in that direction, right? It's very, very different. So this parameter, let's say this thing on the top panel, is the ratio of the perpendicular temperature. So it's this temperature across this way to the parallel temperature, which is dimensionless, which is nice. So it's a dimensionless number, and it's plotted here as a function of the solar wind speed. Okay, so we know that there's, again, slow wind and fast wind. And so you can see that it's evolving the function of the solar wind speed, okay? The panel below that is the ratio of alpha particle temperature. So that these are fully ionized helium atoms in the solar wind to the proton temperature, the average proton temperature. And again, you can see there's evolution here, right? So when the wind speed is high, the value is around 4. When the wind speed is low, it's closer to 1. And there's a transition here, right? It's not a beautiful, smooth transition, but there is a transition. And same with the panel below. This is the speed difference between the alpha particles and the protons. And so you see that in the low speed wind, it's essentially 0. They're streaming together. When the wind speed gets high, they stream differentially. But it's not a beautiful trend, right? There's some data down here that looks a little strange. Okay, so what we did in this paper was to reorganize this data. Instead of plotting it in terms of solar wind speed, we plotted it in terms of what we call the Coulomb number. So this is the same data on the right, but now the x-axis here is what we call the Coulomb number. So this is basically the argument of this exponential. And the motivation for this was a physics motivation. We said, well, what makes the plasma, let's go back to the previous panel, what makes this value 1? Why is this 1 down here? 1 is a magic number in dimensionless units. And the answer is that, or the answer could be collisions, that when you have a collisional plasma, a lot of these kinetic features get washed out, right? The Coulomb collisions, the interactions between particles, will dominate over any kinetics or any adiabatic invariance or that sort of thing. So we said, well, maybe that's what's going on. So there's a simple relationship for collisional isotropization, collisional interactions, right? The time rate of change of the parameter, in this case T perp over T parallel, is approximately equal to the collision minus the collision rate times that parameter itself. And this is true of most collisional relaxation processes. This value of the collision frequency will be different by some orders of magnitude sometimes, or some numerical factors. There may be some other little subtleties, but this is generally a pretty good approximation for collisional relaxation. So if you write this as x instead of T perp over T parallel, kind of generalize it, you can integrate this very simply, and you get a form that's like x goes like e to the minus nu. So I replace dt with r, some distance, let's say the distance from the sun to the earth divided by the wind speed. So this is the time it took the plasma to come from the sun to the earth, to our measurement. And you can write it like this. And so this becomes then a dimensionless number. And if you plot these data versus this dimensional number, you'll see, and this has an exponential form, you'll see that they're very well organized, right? And in fact, this form can be fitted very nicely to an exponential. And this form can be fitted very nicely to an exponential. This one, not quite. There's some process, there's some kinetic physics here that makes it dip back down. I'm sorry, dip back up here at low collisionality. In these plots at this far and the left end, the plasma is essentially collisionless. At the right end, what we call the Coulomb number is large, the plasma is essentially collisional. And so to put them together, you can look at them like this. This is actually the figure that's in the paper. And you can see that the right-hand side looks better organized by the x-axis than the left-hand side does. And that's because we believe the physics here is the physics of collisional relaxation, right? So you start out with a kinetic kind of distribution function near the sun, and as it propagates out to Earth, there are Coulomb collisions occurring, and the denser that plasma is, the more Coulomb collisions there are. The colder it is, the more Coulomb collisions there are, and the slower it is, the more time it has to evolve, right? So you combine all those things together into this variable, and it works out to give you this nice exponential formula. So this is, for me, one of the canonical examples of this, of thinking about the physics of the problem in advance, and then instead of just looking at it in what would be, arguably kind of engineering units, like I said, the plasma doesn't know anything about kilometers or seconds, but it does know about the Coulomb collisions that are happening. And so organizing it that way, can give you some real serious insights. One comment I wanted to make about collision frequencies is we like to say that, and this is something that I hadn't really appreciated until we did this work. We like to say that that the collisional mean free path between the sun and the Earth is about, or I'm sorry, of the solar wind is about 1 AU. That is that a typical binary particle collision will occur once per transit time to the Earth. And that is only true if you take, this is one of the subtleties of the collision frequency, is if you take the scattering angle to be 90 degrees, okay? So if you assume that the particle, that you had a Coulomb collision that scatters, that the incoming particle is scattered by 90 degrees off the target, right? And that's not how Coulomb collisions work. Coulomb collisions are glancing collisions. And so that one 90-degree collision is actually composed of millions of small glancing collisions, right? So in practice, the plasma has collisionally interacted a lot on the way to 1 AU, but if you wanted to ask yourself, well, how many of those little collisions, if you add all those little collisions up to get 90, you'll just get about 1 during transit time. So collisional frequency is something you have to be, this works, but it's subtle. Okay, so another example that I like is, let's go back to the solar wind is bimodal. So the solar wind speed is bimodal again. We already talked about that. There's fast wind and there's slow wind. There's this nice analysis from a paper by Guillaume Lechat, who is, Gaetan Lechat, who's no longer working in the field, but he was a student at the Observatory of Paris. And what he did was take data from the WIND spacecraft, which is at L1 near Earth, in the ecliptic plane, more or less, and Ulysses, which you saw, goes over the poles, and he put them together. And so the top panel here shows the latitude. Actually, it has sunspot number on it too, but the blue, we can ignore Helios for the moment. The red and blue curves are the latitude of the spacecraft. So you see that the Ulysses spacecraft is going, to low latitude, and then over the pole. Here it's in the ecliptic plane. Here it's over the pole. It's going around and around like this. And wind is mostly at 1 AU, so it's just wobbling as the ecliptic plane wobbles. That's the blue curve. The panel below then shows the wind speed in units of kilometers per second. And so again, you see as Ulysses goes over the pole, it sees high speed wind, comes down to the ecliptic, gets back to the low speed, the slow wind, and then over the pole again. Now it's, I guess, over the North Pole. It was South Pole before. And so the wind speed is modulated by the orbit in this way, right? And the blue panel is the wind speed for the same intervals at 1 AU from the wind spacecraft. Okay, and so they're very different when Ulysses is over the pole. But if you plot this as total energy flux instead of wind speed, so now in a unit that's maybe more about the physics, you see that they essentially line up, right? So when the wind speed is high, it turns out that the density is low, right? And so the product of the wind speed squared with the density gives you a number that's the same as the measurement at wind. And so this tells you something really important, right? It tells you that whatever it is that's energizing the wind, it's essentially the same. The underlying source of energy is essentially the same in this fast wind as the slow wind. And so the plasma physics at the base of the corona is probably pretty similar. And so the resulting difference in the wind speed itself has to do with something else, right? And we know now that what it has to do with, in fact, we knew that even, that what it has to do with is the expansion of the magnetic field. The wind that comes out of the poles the magnetic field basically expands more or less like 1/r², just constant flux. For that wind to get down to the equator, to the ecliptic plane, that flux tube has to expand a lot more to hit the ecliptic plane. And so as it expands, if the flux is constant, the speed has to decrease to keep the flux constant. So that's more physics of the geometry of the situation rather than the underlying physics of what puts the energy into the wind itself. So this is another example, I think, of a very nice analysis. And then I'll show you one more from a paper some figures from a paper that I wrote in 2009 that was presaged by a nice paper by Peter Hellinger. So this is now an investigation of the behavior of, again, that temperature anisotropy, that ratio of the perpendicular and parallel temperature. What makes the solar wind kinetic or not as a function of the plasma physics parameters in the wind. And what we did here was take plasma density. So this is several years of density from the wind spacecraft. Magnetic field magnitude, the perpendicular temperature, if you will, thermal speed, and the parallel temperature. And we organized them into a plasma physics derived system. And that is, we plotted the T-perp, the ratio of T-perp over T-parallel, which you saw from the previous paper, changing as a function of collision rate, as a function of beta, the ratio of the thermal energy to the magnetic field energy. And we did that because there were distinct predictions for some universal instabilities in the plasma, namely the mirror instability and the fire hose instability, which are instabilities associated with the ratio of the perpendicular to parallel temperature. And what we found was really beautiful agreement. So this panel on the top is the distribution of that data. So this is just where the data lies in the plane. So it's T-perp over T-parallel, again, the ratio of the temperatures versus plasma beta. High beta out here is really almost like a gas, right? NKT dominates over the magnetic field. The magnetic field is very small, and low beta down here is very magnetized, okay? And these dotted curves that you can barely see there are the instability threshold predictions for the fire hose instability and the mirror instability. And so you can see the data is very well constrained by those instability thresholds, which tells you that there's something there. It's meaningful, right? I mean, there's plasma physics happening in the solar wind. Just by organizing the data in this particular format, you can really see the plasma physics happening. The panel below it shows the ratio of delta B over B, the fluctuation, magnetic field fluctuation amplitude, and you can see that it peaks along these trajectories, right? So where the plasma has expanded and the perpendicular temperature has become large enough, let's say, it starts to go unstable, and it creates a instability, and that instability makes the magnetic field grow. And so the energy of expansion, this is a direct path in the energy of expansion due to the Parker solar wind, right down to the scales, the small scales where things fluctuate. So this was another nice example, I think, of using a kind of a plasma physics problem, not even an intuition, really just a problem, and choosing the right variables to elucidate the problem. And of course, all of these things, okay, maybe not the T-perp over T-parallel, but beta in this case involves the density measurement, the temperature measurement, the magnetic field measurement. In the last case, this Coulomb number, what we also call the collisional age, involves computing a collision frequency, which has a density and a temperature in it, and it needs solar wind speed to get a transit time. So in all these things, you're creating a new data product out of multiple data sets that you have at your availability. Okay, what's next? How much time do I have? 35. Okay, so yeah, so that's my summary of the first part. So in choosing data analysis variables, I argue that the best thing to do is to think carefully about the physics of the problem you're trying to solve. Are you looking for, are you looking at turbulence? Are you looking at an instability? And choosing the variable, creating composite variables that directly address the physics. And so don't just take what comes out of the box. Don't just say, I've got the wind speed and the magnetic field, let's plot them against each other. Think a little bit about what you're looking for and create the right variables from that. And that does involve merging data sets typically. So you have to think a little bit about what cadence to use. Typically, if you have a data set that's sampled slowly, that will determine the cadence of your ultimate measurement. So you'll have to downsample your faster data to the slower data, maybe apply some filters of some sort to project aliasing. In my bottom panel here, or my bottom bullet is, when you become a PI, be pushy about all this stuff, right? So this is one of the things we did on Parker Solar Probe that I think worked quite well, is that we insisted that people sample on the same clocks, so we don't have, as an anecdote, on the cluster spacecraft, we have an electric field experiment that samples, I think, 22 samples per second. And we have a magnetic field experiment that samples at 25 samples per second, or maybe it's vice versa. So they're just off, right, by just a little bit. And all it would have taken was someone to like insist on doing this the right way, and you would have data all the way out to 25 samples per second. But this is one of the things we did on Solar Probe that I'm proud of, is we were pushy about this, and as a result, we have data that can be merged very, very nicely. Okay. So now let's go to coordinate systems. So the same kind of arguments can be made about coordinate systems. Think about the problem you're trying to solve, and think about the physics of it when you're putting your data into a system. Typically, the data will come out of the box as a function of time, right? It's a bunch of numbers that on clock pulses, and so you have the data stream as a function of time. And almost never is that the right way to look at the data. I mean, maybe if you're looking at something on the time scale of a plasma physics problem, if you're looking at, you know, a Langmuir wave in its full carrier, that may be the case, but typically the kind of things we do in, you know, a time series isn't the right thing. Okay, and the data usually comes, you know, the data comes in some coordinate system that's associated with the experiment on the spacecraft, and then it's rotated into some coordinate system that's associated with the spacecraft. The spacecraft will have a defined coordinate system, and then it's brought to the ground, or maybe those things happen in a different order. And then someone will make a coordinate system out of it: geocentric solar ecliptic, solar magnetic, or RTN in the case of Solar Probe. A vector, the radial vector, goes from the sun to the Earth, or to the spacecraft, sorry. Then there's a normal vector to the ecliptic plane, and a T vector that completes a right-handed system. And those are convenient. We can talk to each other about them. We can say, oh, you know, it's at RTN this or whatever. But again, it doesn't mean anything to the sun, to the system. The system doesn't know anything about RTM. GSM is maybe a little different. GSM is aligned with the Earth's magnetic field. That's a little bit more special. Okay, so now I'll give you some examples of coordinate systems that I think have been creative. So the first one that I would point out is what's called the foreshock coordinates. So this goes back to the 70s, actually, to measurements from the IC spacecraft by Kinsey Anderson and his group. And what they found was that when the IC, I think this was IC1 or 2, or maybe it was IMP, actually, it might have been the IMP spacecraft. When the spacecraft was orbiting the Earth, it would fly through a region. So there's Mother Earth in the center. It would fly through a region where it would see very localized sheets of energetic electrons. You know, these are 500 eV to 30 keV or so electrons, very localized in a particular region as it flew around. And so what Kinsey and his colleagues did was associate this with the magnetic field touching the edge of the bow shock. So that magnetic field line, the magnetic field line there, B, is the magnetic field line that just meets the bow shock, the Earth's bow shock, at a tangent point, right? So it's just perpendicular there. And so that's the point. That magnetic field, if you draw it out, that's the magnetic field line that has these energetic electrons on it, or nearby to it. Okay, and they associated that with energization of the electrons right at that what's called the quasi-perpendicular bow shock, right? So that's right where the magnetic field is tangent to the bow shock. So that's interesting, right? That association was made in this paper in 1979. And then a follow-on paper by Filbert and Kellogg suggested a coordinate system associated with that if you drew a line, if you draw that magnetic field line and you had a coordinate that went along a field line, which is called D, actually it's called diff, I think, in the paper, and another coordinate, which is, oh, there's diff, sorry, that is D. Diff is a coordinate that goes from the point of your measurement, or the point of the, sorry, the measurement towards the sun. My cursor is not behaving. From that point, that little spacecraft there, where it says spacecraft, in the direction of the sun or in the direction of the solar wind until you meet that magnetic field line, that coordinate is called diff. Okay, so you have these two parameters, d along the field and diff. And if you write those two coordinates, you can write what's called a cutoff speed, which tells you the fastest or the slowest electrons that can get to that point, right? So at that very edge, say you generate a spectrum of electrons at the bow shock, and they're moving away. As they're moving away from the shock, they're also convecting downstream because the wind is moving downstream at the velocity of the solar wind there. And as the wind moves downstream, only the fastest electrons will make it up to some point near the tangent. Yet the rest of the slower ones will be dragged downstream. And so from this little coordinate system, you can construct what's called a cutoff velocity, a time of flight velocity, and plot it as a function of space. And it tells you that there should be this little feature. These are the fast electrons, the shock generated electrons, and this is the rest of this is the solar wind. And that feature moves closer to the thermal part of the distribution, the deeper you get into this system. So right at the very edge, actually at the very, very edge, when you're upstream even, there are no energetic electrons. As you move deeper down in this direction, this cutoff starts to become lower and you can see the energetic electrons. And of course, this kind of distribution function should be unstable. You put this kind of electron distribution into a plasma, you'll generate waves, Langmuir waves. Okay, and that's what was seen in the Filbert and Kellogg paper. And a striking example of that is this paper by Kasaba. So what Kasaba-san did was take a bunch of data, and I think this was geotail data, and he cast it all in this coordinate system, in this diff and dis coordinate system. So instead of looking at it in RTN or GSE or GSM or something, he said, well, let's use the coordinate system that's the right one for the problem, right? And so here you have diff. This is the distance down into the foreshock, and this is the distance along the magnetic field. And you can see the Langmuir wave, which are the waves that are generated by this, are very well localized along that line. And likewise, there's also in this, it turns out there's actually radio emission associated with this process too. And you can actually almost see the cone, the beaming cone of it here. Not perfectly convincing, but it looks kind of like it. So again, it's an example of taking the data that you have, presumably in some weird coordinate system that was made up by human beings, and putting it into a coordinate system that makes sense for the physical problem that you're looking at. And suddenly it all pops into shape. It's never quite linear like that. There's a lot of trial and error, but okay. Another one that I think is interesting is a minimum variance system. So are all of you familiar with minimum variance at some level? No? Okay, you should read up on it and try it. Actually, it would be a good exercise for your afternoon stuff. So minimum variance is a simple example of what's called a principal component analysis. So this is a way of rotating a data set in some space. Here it's a three vector, so it's a simple, configuration space versus time. You rotate that vector to order the components in terms of some priority. And so in this case, in the minimum variance case, they're ordered by finding a unit vector, which is n hat here, that minimizes this quantity. So basically you're ordering those components into a component that has the least variability in it, a component that has the most variability in it, and then an intermediate one, right? So if you had a 4 vector, you'd have 2 intermediate ones, et cetera. And so that's done by minimizing this sigma squared quantity. And the result of this, and you have to use some math tricks. It's actually not hard at all. The result of this gives you a rotation matrix, okay? And that rotation matrix has eigenvectors, and the eigenvectors are unit vectors that point in the direction of the minimum variance and the maximum variance, and then an intermediate one. It also gives you eigenvalues, and you can use those eigenvalues to see how good your transformation is. But then it's a simple rotation. You get a rotation matrix. And so this is a coordinate system that is, I think, really useful for studying structure in space. And it's useful in part because unless there are magnetic monopoles around or something, we know that del dot B is 0. And that means that there's a direction, a planar direction somewhere in the system at some scale. Okay, so it works pretty well for current sheets. It works well for shocks, some other boundaries as well. And so if you think about a current sheet, a reconnecting current sheet, for example, You know, and how do I have this organized here? So we have a magnetic field. The black lines are magnetic fields. This is from a figure from a paper of Typhons. So the magnetic field here is this black line is going in that direction. Magnetic field down here is going in the opposite direction, right? So we have a shearing magnetic field, right? So this way and this way. And so there's a huge variation in the magnetic field in that direction. And then in this plane, there's a very small magnetic field. Let's say it's a two-dimensional problem. And then in fact, in practice, there will be another magnetic field in the center here where there are currents. Okay, but this is a problem that's well designed for using something like minimum variance. I say down here as well that there are other more sophisticated variants of this thing. Okay, so let's look at an example of this. This is data from again, our friend Parker Solar Probe, taken just a month ago or so. This is the heliospheric current sheet crossing at around 80 solar radii, so around 0.35 AU or so. And so what you're looking at is the top is the magnitude of the magnetic field. Okay, so you see a little dip, which is where the magnetic field shears the most, right? In a perfect system, it would be zero there, or in a perfectly anti-parallel system, it would be zero. This is the magnetic field in the RTN coordinates. So R is away from the sun. So you see we're going from magnetic field pointed away from the sun to magnetic field pointed back to the sun. So this is one of those big current sheets. The red is the magnetic field normal to the ecliptic plane, and green is the one that completes the system. And then below that is the velocity, the plasma velocity in that same coordinate system. So if you take the data between these solid lines and perform this minimum variance calculation, so minimize this sigma squared parameter and compute the rotation matrix, and then rotate both of these data sets into that coordinate system, you see it looks like this. So now you can see very nicely the shearing field. It goes from strongly positive through zero to strongly negative, and it's essentially a simple shear, right? And you can also see in this T direction what we would call the Hall magnetic field. So this is the magnetic field signature associated with a current. So that shearing layer has a current in it, and that current computes or generates a magnetic field by Ampere's law, and you can see that in the result. So that's a second order effect, and it's there in the original data, but it's all mixed together, right? The shearing field is mixed in these two components, and there's some of that's mixed into this one, and when you organize it in the right coordinate system, it's much more clear. And in fact, you can even see it in the ion measurements. These are the ion velocity measurements at a lower cadence. So we don't have the high cadence stuff yet in the right dimension when you rotate the right way. So minimum variance is another example of choosing a coordinate system based on your physics, not based on what NASA gave you, RTN or whatever. Okay, and then finally, I want to talk a little bit about some stuff we've been doing on Solar Probe as well, using what are called PFSS models, potential field source surface models. Does anyone know about these? Good. Okay, good. Some of you know. Okay, so this is basically a way to infer the magnetic field close to the sun using magnetogram data. So you use a measurement of the magnetic field at the photosphere from basically a Zeeman splitting kind of camera system. And so that gives you the magnetic field at the photosphere, which is this first surface 1. And then then you can do if you assume that there are no currents, which is wrong, of course, but it's an approximation. If you assume that steady state, no currents, then the magnetic field must be a potential magnetic field, which means it can be solved from a scalar potential, right? And so you need another boundary condition. You have the inner boundary condition, which is the measured magnetogram data. You need another boundary condition. And the other boundary condition at this outer boundary that we call the source surface is that the magnetic field there is radial. Everywhere at that boundary, it's radial. And so what you're saying effectively is that that's the surface from which the solar wind escapes. Okay, at that point, the solar wind pressure is greater than the solar wind dynamic pressure is greater than the magnetic field energy density. And so the magnetic field is forced to drag out. So below that, you can have closed loops. Back to your question about the streamer belt. Below that surface, you can have loops of magnetic field that close, right? But at that surface, everything has to open outward into the solar wind. Okay, so this is something you can compute. If you have a magnetogram and you make these assumptions, you can actually make the computation and you can compute the magnetic field from that surface, the source surface, down to the surface of the sun. So you can trace a magnetic field line you could take any point on that source surface and trace it down to where it came from on the surface of the sun. So to get the point on the source surface, then you can assume that the solar wind is just blowing out and the sun is turning. So we have a Parker spiral, the magnetic field is twisted a little bit. And so you can invert that twisting and find the point. Your spacecraft is here, and it's got a measured magnetic field. It's got a measured wind speed. You can find the point at 2.5 solar radii, or wherever you put this source surface, where it touches the source surface, and then you can trace it back down to the sun. So you can actually create a kind of coordinate system on the surface of the sun that you can organize your in situ data with. And so we've done that, and this is an example of some time series data from Parker Solar Probe that we published recently. So you can see this is wind speed. This is solar wind speed, and there's these little streams in here, and there's this big bulb of speed there, and then there's another big bulb of speed there, a stream here, a stream there, we call them. And looking at them in terms of time, this is a time series, right? So this is 3 days of data or something, isn't really very insightful. I mean, after you've done this 100 times, you can kind of see what, you kind of know what you see, but at first blush, this I think doesn't bring a lot of insight as a time series. But if you use this coordinate transformation, this PFSS coordinate transformation, so this is from, these are both figures from papers by Sam Badman, who was a student of ours who just finished up a year ago or so. So in this coordinate system, do I have the parenting coordinate system thing here? Where was it? It was here. I forgot to talk to this slide. In this coordinate system, the sun is rotating. So what looks like an inertial coordinate system, the orbit of the spacecraft might be like this, right? It's an ellipse, like Kepler taught us. But in a coordinate system that's rotating, it looks different. It can come in like this, and then it goes through an interval where it's rotating with the sun. Okay, so here it's rotating at the same speed as the sun. Now it's going prograde, so it's going faster than the sun. And then it comes out here again, and it rotates with the sun, and then it goes retrograde again. Because of the orbit of the spacecraft, it gets close enough to the sun that it goes prograde for some intervals. And so it's this combination of this coordinate system and the PFSS that lets us take data like this and map it back to the surface of the sun. So in this coordinate system, the spacecraft comes in from the right. Now we're looking at it in terms of longitude and from this mapping, and it goes through the co-rotation. So here it's rotating with the sun. Then it goes prograde. It's going faster than the solar rotation period. And then here it's rotating with the sun again, and then it goes back out. And using now this potential source surface work, we can take the magnetic field that we measure, or we take the plasma that we measure at the spacecraft, project it back to 2.5 solar radii or so, and then trace the magnetic field back down to the surface of the sun. And so what we see when we do this is that there are distinct coronal holes. This is a coronal hole. This plasma, what we call stream 1, is emerging from that coronal hole. Then here, it jumps to another set of coronal holes. So the magnetic field comes, so this solar wind is coming from these coronal holes, and it has that stream actually has a different property. It has different speeds, different temperatures, that sort of thing. And then we jump here again to a third stream, and we can see a different structure. In fact, the colored stuff here is the wind speed at that longitude. So you see a faster wind here, and it gets a little bit slower. It's much slower over here. So by thinking cleverly about the coordinate system that we're working in, we're actually able to take this, which is a time series data set, which is nice, but it doesn't really tell the whole story. And we're able to say, well, that first stream of wind is coming from this coronal hole, and the next one from this coronal hole, and we can compute the expansion factors associated with those coronal holes, and many other things. I think I'm almost out of time here, so I'm going to go to the last version of this. The last thing here I want to show you is the same technique, this potential source surface modeling and ballistic propagation, now applied to 2 spacecraft. So this is the Parker Solar Probe spacecraft and the European Space Agency Solar Orbiter spacecraft, both orbiting at the same longitude, coming at the same longitude, but from opposite angles. So they're coming around the sun in different directions. And they both see the magnetic field inversion, the current sheet. Parker Solar Probe sees it here. This is where the magnetic field changes sign. Solar Orbiter, which is above it, sees it here. It's much messier. Solar Orbiter is further from the sun. And below, we can do these foot points and see where we are on the sun. And if we put that back into the right coordinate system, we can see on the right. So the right panel here is a similar analysis. And so here you see the black curve. So now this is plotted as a function of longitude on the sun. And you can see that the black curve is the current sheet, is the magnetic field on Parker Solar Probe, and it changes sign right here. So that's where the current sheet is. And so does the green curve, which is the solar orbiter data. That one's coming from the opposite direction. It's coming in like this and going down like that. So we can actually measure the, we have some pretty definitive idea where the heliospheric current sheet is, where the change of the solar wind polarity is, and how thick it is at different distances. And importantly, we can take data. The top panel is data from the solar orbiter spacecraft, which has an instrument that measures what's called low first ionization potential plasma. So it measures the really slow streamer belt plasma. And we can cast that into the same coordinate system and now see what in the previous panel looked like a mess. This top panel is that low first ionization potential plasma. You can see it, it's highly variable, but not particularly striking in terms of physics. But here you can see it's well localized over the heliospheric current sheet. So it's emerging from the streamer belt. And over here, we also see that it's emerging from what are called pseudo streamers, where the magnetic field is from different coronal holes is touching itself. So, okay, and then we can identify separate coronal hole features in the same way we did before. So it's a very powerful technique for understanding the origins of the solar wind, where they come from with an in situ measurement at a distant spacecraft. And again, it all comes about by carefully choosing the coordinate systems. My motivation here is to convince you not to look at too much time series data, because it's just dizzying sometimes. And if you find the right coordinate system, suddenly it all kind of comes into focus the right way. That's all I have. Okay, so the takeaways are: choose your data analysis variables based on the physics that you're working on, and choose your coordinate systems based on the physics too. Don't just take what you get out of the servers. Okay, that's it.
And please use a mic, since we are recording this session. We have a mic back here and also the box mic.
Hi. So in the antenna electronics, like what are the fingerprints by nature that can be seen, and how are they measured or calibrated?
The known unknowns, or the known knowns?
Both.
Okay, let's go back to the problem. So you look at this block diagram that I have here in the upper right corner. So the antennas are pretty simple, right? They're just pieces of metal that you can drive a current in. You sample that current at the base of this thing, and what you're sampling is a voltage you want to understand the electric field in the plasma, right? And that electric field has to go through a sheath. When you put the antenna in the plasma, it charges up, right? It's got sunlight shining on it, and so it emits photoelectrons. So it charges up, and then it attracts thermal electrons back. And the number of thermal electrons that it can attract back depends on how many there are in the plasma. If there's no thermal electrons, it'll just keep charging. And we actually also drive a current onto the antenna to try to control it, to try to stabilize it. And all of that creates a sheath around the antenna, a Debye scale sheath, basically. And so there's some impedance between the plasma and the antenna that's governed by that sheath. There's a resistance and a capacitance, basically, associated with that. And we don't know what those are. We can guess what they are, and we can try to measure them in a diagnostic mode, but we can't really measure them when we're doing science. Okay, so those are kind of unknown. So what you try to do is you try to have enough. For example, if you have a huge input resistance, then you don't care about that small resistance that's varying. And if you have a really small input capacitance, you don't care about the big capacitance that's varying. So we try to do some stuff like that, but it's never completely successful. So you have unknown things there. The analog system itself can be pretty well characterized. You can hook it up to a network analyzer or something and drive signals into it and measure what comes out. And so that isn't too bad. But then when you start connecting cables between things, they all have, impedances associated with them. And so there's a whole chain of kind of things that could be known perfectly well, but are never known perfectly well. And then there's some things that are just not known. So So actually, this is probably one of the worst examples. Electric field measurements in space are terribly messy. Other things are easier.
Just going to have one more question, and then we're going to have a break, and then we're going to have Allison, Jaynes, and then we're going to have a Q&A. So write down your.
Hi, I have I guess a very open-ended question. So Justin Casper had a wonderful example of deriving a new physics-based parameter to look at your data.
Yeah.
I've seen other scientists who, instead of trying to, look at it from a physics standpoint, will, try and let a machine learning algorithm, fit some, like all of the parameters to a correlation of some variable. So I was wondering if you think ignoring the physics and also just using machine learning could be promising.
That's a great question. First off, a little correction. It wasn't Justin who invented that. It was André Marjonet who put it in a paper in 1999. I mean, that's a great question. I'm not like a machine learning guru. I think that there are definitely insights to be had from it, but ultimately, I think you want to be able to. You don't want to be completely empirical, right? You want to be able to trace it back to some. If you're working on data like organizing a giant database of credit cards or something, maybe okay, you can just let the machine learning thing do its business. But I think, since we're trying to do physics and understand, nature, you really want to be able to draw a line back to what the physics is. And maybe there's some. Like I said, I'm not a machine learning person, but maybe there are some nice ways of Monte Carloing things or something with machine learning results and trying to understand how they trace back to. I mean, I know there are people who, Max Tegmark at MIT is actually trying to derive laws of physics with machine learning, right? Like not using data, but actually trying to find equations that way. I don't know. It's a good question.
Oh, okay. So it's quite convincing that this kind of physics-based coordinate and has more physical insight, like visually.
Yeah.
But I assume there's a trade-off when it comes to communicating, like in a lab meeting or even publishing. I assume you kind of have to, like help out the reader.
A little bit. You're right. I mean, we all talk in these units, right? And so, but it shouldn't. I mean, it drives me crazy. Like I'm in a meeting or something, and someone says, "Well, solar wind speed is 700 kilometers per second," and it's like, what's the Mach number? What's that's where the physics is. I think if you have a training and even like a undergraduate level plasma physics class, all this stuff, it doesn't have to go much deeper than that. I mean, you learn the Coulomb collision frequency and in undergraduate E&M. Right. I don't think it has to be too sophisticated, but I think it's nice to think of it as a physicist rather than a space scientist.
They don't have anything. We're investigating the subtle odor.
Yes. Okay. Yeah. So something's on fire. Okay, so let's take a 10-minute break, and we're going to start back quarter after that hour with Professor Jaynes. So is there the tea and coffee is outside? Don't be late because we're late already. I have guest lecturers, 50-ish minutes, a short Q&A, and then we're going to have that hour discussion. So use your notepad or your phone or however you take notes if you have a more detailed question. Many of our guest lecturers are going to be here for the day or potentially later into the evening. Opportunity to pigeonhole them and ask deeper questions over coffee or lunch or whatever. But take advantage of the folks. The afternoon activities are, if you've looked at the schedule, have a sort of a theme based on the lectures during the day. So if you haven't used minimum variance analysis or principal component analysis or other types of rotation linear algebra, you'll have an opportunity to practice and sort of see the benefits of having physics-based either coordinate transformations and or different fundamental units. One of the interesting aspects of a NASA requirement is for an instrument, they want to know, your magnetometer, nanotesla, what's your dynamic range, what's your resolution, what's your cadence. But for many studies, I want to know Poynting flux or something like that. And I'm going to need both E and B, right? But do I make that as a measurement parameter in a mission STM? And as Stuart was saying, forethought, if most things are at intervals of 16 Hertz sampling rate, probably everything should be at 16 instead of having one at 10 and one at 20 and one at 16, because there can be a lot of these merged data sets that are close but are not quite there. And when you think about like Poynting flux, shifted in a little bit of phase can have a big difference. So I'd like to have Allison, Jaynes come on up, and if you could introduce yourself a bit before you dive in. But Allison is on a sabbatical, so thank you very much for coming by, but just started this weekend, I think.
How's the mic? Good? Okay, awesome. All right, so I'm gonna try to not stand on this stage because I don't really want to. We'll see if this works, if I can stand down here and talk to y'all. So I'm gonna talk about calculating quantities in terms of energetic particle dynamics in the magnetosphere. I wanted to go over some science first. So we're gonna start with like the main mission that I'll talk about and some of the science discoveries that we've made with that mission. And then at the end, we'll talk about actual calculating of quantities and what that means and how, all the little imperfections that go into calculating energetic particle detector fluxes. I'm going to start with an introduction to myself, just kind of like Stuart did. And that's going to begin with my career path, just to give you an overview of kind of what I've done with my life so far. I got my PhD at the University of New Hampshire with Mark Lassard. I did sounding rockets. And similar to Stuart, I had my thesis rocket blow up, in the air, not work, not get any data out of it. So after, 2.5 years of working on an experiment, building it with my own hands, and then putting it onto a sounding rocket and hoping that it will give me this beautiful data for my thesis, I got 0, right? I got nothing. And so I had to quickly just, pivot, look at data from a satellite mission I did in the end. And that was what I wrote my thesis on. So, it's a good lesson. It's a good lesson to fail and to have that, that feeling of just utter, I have nothing to show for the last 2 years of my life. And then to bounce back from that. So I learned a lot from that process. And a lot of us have gone through this failure mode over and over again. so from there, I went on to do a postdoc at LASP here in Boulder. So I was just down the road at LASP for like 5.5 years. And I was first a postdoc there, and then I was a research scientist. And then I applied for a position, a tenure track faculty position at Iowa. And I got that position. I was tenured last year. And so that's kind of where I am right now, career-wise. And it's sort of a dream job. I love teaching. I love science. I love students. I love advising. And it just kind of encompasses all of those together. So it's been really, really great. I am co-investigator right now, currently on the Voyager mission. I have been co-investigator on the Van Allen probes mission, although that mission has been decommissioned and it's over now. And I'm an instrument team member on the MMS mission. I have worked on CubeSats, rockets, sort of multiple in those platforms. And I'm currently the Wendell F. Miller Distinguished Professor. So I just got this named professorship at Iowa, and also a big mid-career award that they give out. And I'm telling you all of this because despite this long list of like, I've had this cool career, I've had these great awards and accolades given to me, I still find myself struggling all the time with imposter syndrome. And I'm sure you all know about this and you've heard about it and you felt it before, but I just want to tell you this because I think a lot of people that are in these positions that look so great from the outside don't readily admit that they are also constantly struggling with, like, should I be here? Am I good enough? Do I know what I'm doing? You know, why did I get this position and not someone else? Why did I get this grant and not someone else? And you start to doubt yourself, and that kind of creeps into your life and your work. And there's ways to deal with that. I think everyone's a little bit different on how they deal with imposter syndrome and how they kind of get over that. The way that I deal with it is I do a lot of things that involve activism, inclusive spaces, student work, and I just throw myself into those activities. And those are so real and tangible. I mean, stuff like this school where I'm going to get to know all of you, I'm going to form all these relationships, I feel like I'm going to have an impact on your life. And that's like real tangible stuff, right? And I know that I'm making a difference. And so then when I go and submit a paper and I get terrible reviews and I'm doubting myself, I can think back to the times in which I've had these one-on-one relationships, or I've had this impact on someone's life, and it makes it, you know, better. It makes it all worth it. So this is how I gain resilience to deal with that constant imposter syndrome that's in my head. If you ever want to chat about any of this stuff with me, there's my contact information as well. Okay. So we're going to start to talk about radiation belts, energetic particles in planetary magnetospheres. And I'm going to start with an overview of the Van Allen probes mission, because that's mostly what I'm going to discuss data from today. So just to say this point that Earth's magnetosphere is a very efficient particle accelerator. There's a couple that are even better in our solar system. Does anyone know what those are? Besides Earth? Yeah, Jupiter is one. Jupiter is a real heavy hitter, right? You can really accelerate particles within that magnetic field, and Saturn as well. Okay, but Earth is pretty darn good. So we study Earth because we have Van Allen probes, or we had Van Allen probes at Earth for 7 years, orbiting in this sort of two spacecraft following each other in this similar orbit. Sometimes they were farther apart, sometimes they were closer together, but they were basically cutting through these radiation belts over and over again 3 times per day, and you had this 2 spacecraft view of those radiation belts constantly. So that was very, very nice to have for our 7.5 years. It's over now, but we did have that great data. And the top picture here is showing you all of the dynamics that are happening in a trapped magnetic field to trapped or quasi-trapped particles. And you can see that there's this, gyration motion, there's little spirals happening. You can see there's a bounce motion as these particles go to stronger magnetic fields near the poles and then turn around. And if you were to have a really accurate picture of this whole thing would drift as well. Electrons drift east, ions drift west. And so you have this drifting motion on top of all of these motions. So it gets really, really complicated. and we try to disentangle what's going on in that space. Oh yeah, because I'm from Iowa, I have to tell you this. So University of Iowa is where the discovery of the radiation belts took place. This is a picture of a few notable people there, William Pickering on the left, James Van Allen in the middle, and then Wernher von Braun on the right. And they're holding up Explorer 1, which was the first US spacecraft, and it had a scientific payload on it, and it took data, and later that data was analyzed to see the radiation belts in existence. This is where I work at Van Allen Hall, so it's pretty cool that I work on radiation belts, and it was discovered there. I wanted to point out that Sputnik 2 was actually launched a few months before Explorer 1, and they also had a radiation measurement on board, but they did not get their data transmitted to them. It was actually telemetered down to Australia, I believe, and they captured that data in Australia. And the Soviets refused to work with the Australians, and they didn't want to allow them access to the data, and the Australians didn't want to just give them the data up without being able to collaborate on it. And so instead of the Vernov belts, which is what these should have been, it's now called the Van Allen belts. Okay, so always be willing to collaborate with people. You will get better results every time. Don't let this happen to you and fade away into the recesses of history. Okay, this is maybe apocryphal, but it was said that when the data came down from Explorer 1, you know, it's definitely apocryphal, but you know, Van Allen was sitting at his desk looking at the data and then just exclaimed, "Space is radioactive," which is probably not true, but they did figure this out, right? So this was the first discovery of anything in space, and we happened to discover those radiation belts. Okay, so fast forward to, we've learned a lot since then. We put up this mission called Van Allen probes, and we wanted to really discover, you know, a few very distinct things about this system. And so the fundamental questions, I think, for energetic particles specifically would be, where do these highest energy particles come from? How are they transported through that planetary magnetic field? And then what happens to them, right? Where do they go in the end? They have to go somewhere. They can't just stay there and build up and build up. They have to go somewhere. So we're going to start by talking about where they come from. And I have a question for you, which is, let's say outside of the magnetosphere. So we already know that they can be created inside the magnetosphere, right? You can pump up the energy in different ways inside the magnetosphere. But where do energetic particles come from outside the magnetosphere? Yeah. Yes. Exactly. Yeah, say that last one again. Yeah. Okay, so we've got galactic cosmic rays, we've got anomalous cosmic rays, and that third one comes from the sun, right? So we say solar energetic particles or you know, SCP events. And so I'm going to start with just talking about those solar energetic particle events, because that's sort of a source that's outside of the magnetosphere, and we just end up seeing it kind of wash in over the magnetosphere. And we can detect them from within Earth's magnetic field, but again, they're not created inside Earth's magnetic field, right? They're created at the sun at flare sites, or within a CME or a shock, right, associated with a CME. And we can just basically see that as data while we're on orbit in our Van Allen probes orbit from within Earth's magnetic field. So here's a couple of examples of what these SCPs look like from inside Earth's magnetic field. So up here, you can just see a few different events that are being shown, and the events look very different depending on which SCP we're looking at. Some of them up here only access the very top of the magnetosphere. And the way these plots are set up, I'm sorry, you can't see those labels. It's really bad plotting or why it does that. Okay, So it's really bad plotting form to not be able to see what the label axis says. But this is L shell, or basically distance from Earth in Earth radii. And so down here, you're really close to Earth's surface. And up here, you're at about 6 RE away, okay? So when we're going through our orbit, we can measure these energetic particles, and you see this little blob of stuff, and it only reaches down to about, 5 Earth radii. It doesn't get any closer than that. Here's one that we can see at a different time, where we end up seeing penetration all the way down to, L of 3 or 3.5, something like that. And then here's another one where we end up seeing access only down to, again, sort of mid-range L shells, but mostly at the high L shells. So these events look very different depending on which one you're looking at. We can compare them with ACE solar wind. So out at L1, we can compare that with the data here and see that we are looking at very similar features. We're just seeing them kind of wash into the magnetosphere. There's a couple of outstanding questions. We don't really understand the cutoffs or how far in these particles can get yet. So we're still working on those questions. But it's really cool that we can see them with Van Allen probes. So SCPs can get trapped close to Earth within the magnetosphere, and we basically see them forming this inner radiation belt. So they can come in, they can get trapped or not, but they can often get trapped, and they sort of diffuse inwards slowly over many, many months or years, and they kind of form this inner radiation belt. Let's talk about the outer radiation belt. And the outer radiation belt is primarily high energy electrons when we're talking about energetic particles. So high energy protons are in the inner radiation belt. High energy electrons are going to be in that outer radiation belt. So let's look at those. Again, we have the same plotting format. Here you can read the axis at least a little bit better. And this is L shell again on the y-axis. And you can see from close to Earth, I think it cuts off at L of 2.5 and all the way up to L of 6.5. And these panels are sequential in time. So we're going from September 2012 all the way to October 2019. And this is showing electron flux for 4.2 MeV electrons, okay, highly energetic. These are very high energy guys that we're looking at. And the 7 years, if you look at it as a synoptic view here, it looks very different, right? If you were to just look at from 1 month at a time to a different year at a time, it would look very, very different to you. And you couldn't really make a general statement about what the radiation belts are like, because you have to see it in this full 7-year view to really understand the changes that the radiation belts go through. So let's look at a couple of these. Yeah, we had this really extremely quiet period through 2013 and 2014. This coincided with a government shutdown, so we used to joke about how the funding for the radiation belts was lost because they just disappeared. And we were honestly a little concerned because we thought if this is what the rest of the mission looks like, it's kind of sad, But luckily, things changed, and our spacecraft were healthy enough and they lasted long enough that we were able to see a bunch of dynamics happen after this. We can see remnant belts appear regularly. So these are sort of overlapping outer belts. So kind of two distinct outer belts. You can make it out there and over here during this event. There's a number of them where you can kind of see a lower L shell outer belt and a higher L shell outer belt at the same time. So we call those remnant belts or double outer belts. And we saw those pop up a number of times. We also had these really nice quiet periods, which are valuable to have because we can see what happens during the slow decay of these particles, right? We're going to talk about where these particles go, but here we're able to observe this nice slow falling off of the particles, whereas when you have all these dynamics, it covers that up and you can't really tell the acceleration periods from the decay periods, but I like the slow periods because we can really focus in on the decay. At the end here, sort of in the latter 3/4 of the mission, you can see that we had a lot of high-speed streams picking up, and these give us repeated storms over and over and over again. And so we end up seeing this like cyclical acceleration that happens constantly over and over again. This is going to be probably due to coronal hole that's rotating on the sun. and it just keeps pointing towards Earth every 27 days or so. So we end up seeing like this cyclical high-speed stream, and it just keeps coming around, and then 27 days later it comes around. And if you have 2 coronal holes on the sun doing that, then you end up with like about, 2 big acceleration events per month. So it's interesting that we saw this cyclical stuff happen. Okay, so where do these come from? This is sort of the big question that Van Allen probes was supposed to answer, and I don't know if it really has answered it, but this is what the mission was set out to do. So there's 2 dominant acceleration mechanisms that happen inside of a planetary magnetosphere to get these energies up to our high, relativistic and ultra relativistic ranges. The first one is called inward radial diffusion. The second one's called local acceleration. I like this cartoon because it just gives you like a view of what these 2 mechanisms look like, but they're both driven by wave particle interactions. Okay, so that's the basis of all of this, is wave particle interactions happening inside that magnetosphere. This is just a plasma wave example. We see lots of plasma waves in the magnetosphere. Maybe I can have y'all raise your hands if you're familiar with sort of the scope and range of plasma waves inside of a planetary magnetosphere. Okay. Okay. Good, Stuart, you know them? Okay. Maybe I'll show you those in a second too, if you're interested, just to see like the range of different plasma waves. Okay, great. But basically we can have interactions between particles and waves, and that can lead to both loss and acceleration. And so we're talking here about this acceleration mechanism. So during this acceleration mechanism, we're going to see that inward radial diffusion is very different than local acceleration. Inward radial diffusion, this is driven by what we call ultra low frequency waves, or ULF waves. This results in stochastic changes in L shell. Okay, so that just means kind of little kicks in L. And so inward implies it's kicking inward, right? You're moving your particles inward in L shell. What happens in a planetary magnetosphere as you move farther in towards the planet? What happens to the magnetic field? Yeah, it goes up, right? And so we end up with betatron acceleration of our particles. You're just moving them from a weaker magnetic field to a stronger magnetic field. Let's assume conservation of adiabatic invariance, and you end up with higher energies, right? You just move them from out to in, and they energize. And that's where we get some of these ultra relativistic energies coming from. Okay, so that's sort of easy to envision. They're coming from this outside source, and they're moving inward, and their energy is just bumping up as a result. A local acceleration is a little bit different. So instead of taking something from an outside source and moving it inward, you're actually somehow changing the energy in place. Okay, so you're changing that energy in that same location. And these are driven by VLF chorus waves. And those chorus waves are interacting with the particles at that same location, not a different location. And there's stochastic changes in energy. So there's energy diffusion or momentum diffusion, we call it. And that has the effect of actually bumping up the energy in place and changing the energy of those particles, not because they're moving in magnetic field, but because they're gaining energy from waves, basically. The waves are giving their energy over to the particles. So because that source is happening in place, we kind of see it as this growing peak, right? They start off as low energy and they kind of grow as high energy, but they're not coming from an external source. We see it happening in place, and that's why it's called local acceleration. Okay, so the question that I think people have been trying to answer for a long time now, but we tried with this mission is, when and under what conditions is each of these mechanisms dominant over the other? And, when not does one happen versus the other, but when is one dominant over the other? Because they're both happening at the same time. Just to go over a couple of examples of that, we had a paper in 2015 that looked at this September 2014 storm and saw that by all accounts, it should have produced high energy particles, but it didn't. Okay, and what was the reason why it didn't? So these are also interesting cases to go look at when you're doing your research. Is something should have happened. The hypothesis is that, you know, this whole chain of events should have taken place, but there was something off, something missing, and your job is to sort of figure out what was missing in that case. In the case of the September storm, there were no low energy particles to create VLF waves, and because there was no VLF wave growth, there was no wave particle interaction and no local acceleration. So we kind of came up with a schematic to show how each step in the process has to happen, sometimes at the same time, sometimes one after another, in order to get all the way up to your building up of your outer radiation belt at these high energies. That was local acceleration. We've also looked at periods of time where we see this inward diffusion. Look at that plot there. You can almost see by eye the inward diffusion, right? You can see those energetic particles coming closer or going lower in L shell as time went on. And so this is a really nice example of just kind of seeing that inward radial diffusion. And at higher energy channels, you didn't see these particles, and then you saw them, and then at an even higher energetic channel, you saw them later, and a higher energetic channel, you saw them even later. So you could just kind of watch them march in and energize as it happened. Okay, so I'm going to, I had this as a backup slide, but let me kind of go there right away. I think we want to talk about plasma waves really quick because I wasn't sure if you'd gone over this material yet or not. So this is a cartoon and then real data of plasma waves in the magnetosphere. The cartoon is kind of a canonical schematic that a bunch of people have tried to redo and make it cleaner and make it more obvious. But this is basically adapted from the first one, which was Richard Thorne, 2005. And it's showing the overlapping regions of plasma waves in an equatorial cut of the magnetosphere. So you've got the sun on the top there for some reason, and then the tail down at the bottom of the plot. And then you can see these shaded regions with the labels on them. And we've already talked about ULF waves or ultra low frequency waves. Those can be local or global. They kind of can happen everywhere all at once. So that's why they're depicted like this. Chorus waves tend to happen on the post-midnight into the dawn sector. So that's that big green blob here. We have enhanced emic waves. They can happen anywhere, but we have enhanced emic waves over on the dusk side here. We have a dense plasma sphere close to Earth where His waves can occur. Those are VLF, very low frequency also, but they're called His instead of chorus, and they act a little bit differently with our particles. And then we have magnetosonic or equatorial noise, which is sort of this boomerang here, and it overlaps a bunch of the other wave populations. Okay, so things are kind of happening all at the same time in different places occasionally. Now on the right is a spectrogram of one orbit of the CRESS satellite, which had a wave receiver on board and was looking at the whole range of plasma waves that you can see just through one orbit through the radiation belt. It's kind of similar to Van Allen probes. So now we're looking at labeled waves on a frequency versus time spectrogram. And so frequency is over here on the y-axis. And so ULF or ultra low frequency is below the range of this plot. You can't even see them on here. Okay, so consider them way, way, way down low. Then as we go up in frequency, we're looking at magnetosonic waves. We're looking at His waves around the same frequencies. These are these time domain structures or electrostatic structures here that are not labeled because we didn't really understand them all that well back then. This is Whistler mode chorus waves, so VLF waves, a little bit higher frequency. We're looking at ECH waves with harmonic structures that go up even higher than that. You can actually see through the course of this orbit the cutoff of the plasmasphere. So it's this sort of vertical line here, and you can see where you exit the plasmasphere and go into the outer magnetosphere. And then over here, you're going to come back into the plasmasphere. And inside the plasmasphere, you can have His, but you don't have it outside the plasmasphere. So there's a lot of cool stuff going on in this plot, and it kind of gives you the whole range of plasma waves that can exist in the magnetosphere. Questions about, yeah. Yeah. Gone, yeah. Yeah, so that's a good question. How did Van Allen probes? Yes, yes, I just about to. How did Van Allen probes lead to more understanding of EMIC or EMIC and chorus waves? ULF waves are everywhere, right? All the time. We can see them pretty constantly, but EMIC are concentrated, or at least not just on the dusk side, also at higher L shells near the day side magnetopause. So there's sort of, this picture isn't everything. It's not comprehensive, but how was Van Allen probes able to look at new discoveries about those two wave populations? So chorus waves are actually seen almost all the time. They're not just in the dawn side. That's just when we see them most intensely. We see them most often, but we can see them around in all magnetic local time or every clock angle around this magnetosphere. Same with EMIC waves. They show up kind of all the time in random locations. We can see them in plumes. We can see them on the edge of the plasmasphere. We can see them at the day-side magnetopause. This is meant to show you kind of where the most intense interactions take place, but it's not meant to say like this is only where these waves happen. Yeah. So we did observe, there's so many detailed discoveries about these two wave modes from Van Allen probes that we were able to deduce. Yeah. Question? Yes, so the question was, chorus waves can accelerate particles, they can also decelerate particles. So when particles undergo momentum diffusion, you can think of them as either gaining energy or decreasing in energy. And these both happen due to chorus waves. Another thing that happens is pitch angle changes. And you can change the pitch angle with chorus waves to be more field aligned, and therefore these particles go deeper in the atmosphere. And if they go deep enough, they hit the atmosphere and they never come back to the trapped magnetic field. So we can lose particles this way as well. So it's very complicated because you have all these things happening at once. It depends a lot on the energy of the particle, the wave intensity, the cold plasma background of this magnetosphere. So what's the background parameters that you're operating in? What's the density? All of this plays into what the interaction is between the certain particle and the certain wave. Some particles will have one interaction with that wave, and a different set of particles will have a different interaction with that same wave at the same time. So it just gets to be very, very complicated. We do lots of diffusion modeling to try to understand which energy ranges are going to have energy lost, which energy ranges are going to have energy gained, and whatever our density is, maybe how intense those interactions are. So good point. Yeah. Okay, let's, nope, this is all my back up slides. Go back to where we were. Okay. So I'm not gonna have enough time to go through all this. Yes, so there's also shock-induced acceleration that happens. This can be prompt acceleration, like is shown in these little red blobs that show up in all these energies at once here. And this is when you have an interplanetary shock impact in the magnetosphere. You can cause very strong electric fields deep into the magnetosphere, and therefore you can energize particles that way. So this does happen, not very often because we don't get interplanetary shocks that end up propagating, that deep into the magnetosphere, but it can happen, and we've seen it happen with Van Allen probes. Yeah, I'm going to skip some of this. Okay, this is an interesting question. How are geomagnetic storms related to these changes in the electron acceleration? So here's a plot from Jeff Reeves 2003 showing the response of 1 to 3 MeV, so high energy electrons, in the outer radiation belt, just kind of added up all of them together, over 11 years or 276 storms. Okay, the red is an increase, which means after the storm, there were more 1 to 3 MeV electrons. The green is no change. So no change before and after the storm. And the blue is a decrease. So after the storm, there were fewer 1 to 3 MeV electrons than before. Okay, so I'm going to ask you this. What does this plot tell you? If you were to just look at this plot and look at these results, what conclusion would you come up with from this? Yeah, Austin. Okay. Okay. Yeah. Anything else? Yeah. Mm-hmm. Right. When is the pre? When is the post? How do you define that? Yeah, very good. Yeah. Yeah, interesting. So what is the preconditioning of the magnetosphere before the storm happens? This plot doesn't tell you that, really. Okay, I like Austin's comment the best because that is what the community took away from this result for many years, is like, well, it doesn't tell you anything. Like, it can increase, but it's also likely to decrease, and it's also likely to cause no change at all. So, what happens? And I think the big takeaway from this is, and this was Jeff's kind of, pithy comment on his study, was he came up with this saying, if you've seen one storm, you've seen one storm, rather than if you've seen one storm, you've seen them all, right? Because they really are just so highly different from each other. And I would say to this day, we still don't really understand why we can't reproduce better results, right? Why can't we predict if a storm is going to give us more content, less content, or the content's going to stay the same? So I would like to present this hypothesis, is that substorms and not storms are really the critical piece. So substorms happen every day, but during large geomagnetic storms, you can have stronger substorm activity, and they can be more frequent over the period of that storm. And if we look at the data a little bit more carefully, we're starting to see that actually substorms, these periodic, every few hour things that happen every day in our magnetosphere, are really the things that are building up that radiation belt and those high energies. So this is a plot of trying to look at our electron flux, the same quantity, versus solar wind speed. And you can see that at high solar wind speed, yeah, you tend to get really high flux, right? But at low solar wind speed, you can also get high electron flux. So it gives you this triangular distribution where, like, yes, if you have high solar wind speed, you're very likely to have high flux. But if you have low solar wind speed, you can get any range of electron flux, even up to the very highest levels that you would get during high solar wind speed. So it's solar wind speed is not giving us that crucial parameter that we need to predict what's going to happen. But if we look more at the substorm index, for example, so AL here is a common substorm index based on ground magnetometers at sort of auroral latitudes. And if we look at AL, we get really nice high correlation out in the outer radiation belt. So this is L shell here. This is mu, which is the first adiabatic invariant, or trying to disentangle energy from magnetic field strength. And we're looking at higher correlations out here in the outer radiation belt at like 4, 5, 6 with AL than we are with SIM-H, which is DST, or a measure of geomagnetic storms, right? Out here in the outer belt, we're not getting high correlation with our storm index, but we are getting high correlation with our substorm index, which means that it's probably more important. Substorms are more important to predicting whether or not we're going to have electron flux changes and what those changes are going to look like. Okay. All right. Gosh, I'm only on my second question. I'm going to try to go a little bit faster. This is just an overview of like, how do we now transport these particles around the inner magnetosphere? So we've created them, we've accelerated them. now what happens? And we've already discussed a little bit about this, that we have inward diffusion. We can also have outward diffusion. So this depends a little bit on the profile of our particle, what we call phase space density, or again, trying to place our particles in adiabatic invariant space rather than energy and physical location space, because those obscure the actual quantities that we're interested in, which is the phase space itself. So looking at, mu, which is a function of the energy, k, which is a function of the bounce motion, and then L star, which is a function of the drift period. And we're looking at, in those quantities, we're looking at profiles in this quantity L star, which is sort of like Earth radii, right? Sort of like distance from Earth. And we're looking at these profiles and seeing that some of them have positive slopes, some places they have negative slopes, and where you are on this profile when you get sort of interacted with by plasma waves, that depends on where you're likely to go from there. Okay, so if you're on this side of, the earthward side of the peak over here, if you get a little bit of kick by ULF waves, you're gonna tend to go inward, right? You're gonna tend to go diffuse inward along this profile. If you're on this exterior part of the phase space density gradient, so out here, and you get a little kick, you're gonna tend to go outward. So it really depends on where that particle is on that gradient. And you're gonna just tend to go towards the lower gradient, whatever side you're on. So that can result in inward and outward radial diffusion. So say there's ULF waves happening everywhere at once here. What's the overall effect on these profiles? What do you think? So there's ULF waves happening everywhere, all L stars, all L shells. What ends up happening to these profiles? Yeah. Sorry, say again. Yeah, okay, they move down, and why? Yes, to the left and the right, right? It's kind of like a smearing out of a peak in a profile, right? So it's just like any diffusive process. You're going to try to get rid of those peaks. You're going to try to smooth things out. When you drop your cream in your coffee, it ends up going to lower areas of lower concentration over time. So that's exactly what's going to happen here. So you throw a bunch of waves at this, and it's just going to diffuse particles both to the left and the right of the peak, and those peaks are going to come down over time, and you're going to kind of spread everything, smear everything out. Yeah, so we see that happen all the time. We can study this, and we can look at the rates of inward diffusion versus outward diffusion based on different parameters and try and predict what is going to be the end result. Okay, I'm going to skip this part and go to what happens to the particles. Okay, so they can't just stay there forever, or we just have this buildup over time and eventually, have this ridiculously full radiation belt. That's not what we see. If you remember that movie there, we saw the radiation belt change over time. So we have loss mechanisms in addition to our acceleration mechanisms. So we have a couple of different loss mechanisms. I would say the main two loss mechanisms are like inward or outward, right? So you can get lost to the atmosphere, or you can get lost to the magnetopause, and you leave Earth's magnetosphere completely. All right, so the ways that we can lose to the atmosphere, we can get pitch angle scattered, and I'm not sure if all of you know kind of what that means. So just briefly, the pitch angle is that as that particle is bouncing, it has a certain velocity component along the field line and a certain component perpendicular to the field line. And if it gets enough velocity along the field line, you start having large bounces, right? Starts going closer and closer to Earth's poles. If you get enough parallel velocity, what happens? You get close enough to Earth's pole that you hit the atmosphere and you get a collision, energy goes somewhere, does something like aurora, and you never see that particle again, right? So these energies are not going to produce aurora, but something happens, the energy gets deposited into the atmosphere and the particle doesn't return. So that's sort of our end case of our pitch angle scattering, is that loss to the atmosphere. And this can happen with interactions with EMIC waves or with interactions by VLF Hiss waves and VLF chorus waves. And we have a loss to the magnetopause as well. So that's the outward direction, right? So we've just talked about outward radial diffusion. If you go outward far enough, you're going to leave the magnetosphere and you can go through the magnetopause and sort of end up in interplanetary space, and then they're just gone. You know, they don't affect Earth anymore. And this can happen during periods of outward radial diffusion, strong outward radial diffusion, or sudden magnetopause compressions, right? Because if you have a nice bubble of your magnetosphere and it suddenly gets compressed by like a solar wind transient, then all of a sudden field lines that were closed are now finding themselves open to the solar wind. So that happens all the time as well. Yeah, so some of the mysteries that we've been trying to figure out with the data, one of them is these dropout events, and this is what one of those dropouts looks like. So I just made this quick plot to show you what it would look like. The dropout is when you lose particles at all energies at the same time, and they're just gone. And you know, you can see here where this sort of looks like just someone took a bite out of the radiation belt, and there's this missing piece. And then there's a reacceleration maybe that happens, not always, but sometimes happens afterwards. But the question is kind of what happens to all those particles during that dropout. It can sometimes be adiabatic effects, meaning the magnetic field compresses and then relaxes back outward. And so the particles move with the magnetic field. So they can look like they're gone for a second and then they can come back later. But other times we look at the data and we understand that it's not adiabatic. They really are gone. The particles just left. We don't see them in phase-space density, which means they can't be there. They're gone. And so one of the big questions is like, what happens to these? We've looked more recently at this effect of EMIC waves on just strong depletions across a range of energies all at the same time. And we see in our phase-space density profiles these little dips that are indicative of local loss. So in contrast to local acceleration, we saw the peak before, where it looked like things were accelerating in place. This is like loss is happening in place. Okay, so sudden loss that's happening in place. If you go from the blue traces to the red traces, this is just a matter of hours, and you're looking at phase-space density, so all the adiabatic effects are accounted for. And there's real loss, right? There's this real dip in the gradient here. And something's happened to those particles. They're just gone. And we think that it's EMIC waves that are just suddenly and quickly scattering into the atmosphere, and the particles are gone forever. Okay, we can look at EMIC wave distributions. So here's back to your question about where are the EMIC waves. They're actually all over the place in MLT, so around the magnetosphere here. We can see them at all locations. This isn't showing you, but they happen to be more intense over on the dusk side. But we do see them everywhere. And when we see them, we have a very characteristic change in pitch angle distribution. And we're gonna talk about pitch angle distributions this afternoon, and you're gonna create some pitch angle distributions from data. But pitch angle distributions are showing us essentially the trapped particles at 90-degree pitch angle. Those are the ones gyrating perpendicular to the magnetic field, and the ones that are more likely to be lost at these low pitch angles at 0 and 180. And those are the ones that are more with their component along the magnetic field line. And you can see that when we have EMIC waves, as shown in the arrows here, we end up with a narrowing of the pitch angle distribution. So we're only left with near 90-degree particles. We've lost a lot of the ones, say greater than 135 or less than 45 degrees. They're just gone. And so we see this narrowing of the pitch angle distribution. It's a very clear signature of EMIC wave activity. So it's kind of cool. We can look at the particles and we can even say there are waves happening, even if we can't see the waves themselves because of this signature. Okay, and then this is another cartoon. I like cartoons, but this is a cartoon showing that magnetopause compression. So let's again look at a gradient in phase space density over L star, right? So we've got this increase in our population, and then we've got this, maybe a positive gradient out to the magnetopause, or maybe a slight negative gradient out to the magnetopause here. All of a sudden, we have a storm come in, a solar wind transient, maybe it's a CME, and we have this magnetopause pushed inward suddenly due to that solar wind pressure. So we've got this magnetopause move in suddenly. Everything on the outside of that is now lost, right? All these particles are gone. The magnetopause will relax back outwards, right? So it'll move back out to higher L shells. But what you're left with is this like peaked distribution instead of this nice flat or slightly negative gradient that goes out to the magnetopause, right? You're left with this very highly peaked distribution. And what we said earlier, what happens over time as diffusion takes place is you just kind of smear it out, right? So you're going to push things to the left and the right. And then that overall peak is going to, as a result, come down. And so you end up with a net loss. And if you were to fly a spacecraft through this, you might just see like lots of particles before the storm over here. And then maybe you fly through like 9 hours later and you see a lot fewer particles. And it could be due to this magnetopause compression and then outward diffusion and this overall net loss. Okay, a couple other things I wanted to talk about with energetic particles. We do see energetic precipitation that's associated with a type of aurora called pulsating aurora. This is one thing that I study very, very enthusiastically. And so this is a video of pulsating aurora from all sky image cameras across North America. And you're looking at pulsations happening from, all the way from the west coast of Alaska to the east coast of Canada, across the entire swath of North America at the same time. And this particular event lasted for hours of time. It lasted until dawn. The sun came up and the cameras were turning off and it was still going, right? So this is not uncommon. Pulsating aurora is very common. It can be long lasting and it can be like widespread like this. So we think it constitutes a large amount of energy that gets dumped into our atmosphere all the time. But the really cool thing we found out recently is that pulsating aurora can contain a high energy tail of precipitation. It doesn't form aurora, okay? So these high energies will not form visible aurora. But we are measuring those particles in situ now, and we're seeing that the high energies come along with the aurora. Okay, so we can't see them by eye, but they're there. And this is really cool because it means that, if you're thinking of the energy spectrum of aurora, it's now extended way out in energy than what we used to think was true. We even see MEV energies associated with this type of aurora. Yeah, question. What is a pulsating aurora? So it is a type of sort of diffuse and dim aurora that happens in large patches that turn on and off. And we know this to be associated with VLF chorus waves that are also quasi-periodic in the magnetosphere. And so we see basically chorus wave interactions that are dumping particles in this on and off fashion out in the Earth's magnetic field. And in the ionosphere, we can see that as pulsating aurora with patches turning on and off. It's not your discrete aurora, so it's not your arcs. And it's not your substorm aurora, which is what everyone goes off and photographs when we see, when you get alerts on your phone about there's a space weather event coming. It's a lot different than that. And it's caused by these chorus waves in the magnetosphere. And it happens all the time, but it can be energized after substorms. Where are they in these plots? So it's all the flickering that you see taking place. So this is sped up in time. They don't actually flicker this fast, but if you watched it in real time, it would take forever. So all that flickering that's happening across North America there's a lot of clouds in there. So there's a lot of things that are obscuring the aurora, but there's pulsating aurora happening everywhere in those flickers. So the cool thing about this is that with these energetic electrons coming into our atmosphere, we see that they affect not just loss from space, which is interesting, but they're actually affecting the atmosphere itself, the neutral atmosphere. And they can get low enough in the atmosphere that they are producing chemical constituents that can degrade ozone. And so we are seeing ozone losses. So this is what the simulation shows here. Ozone losses in the blue that last for months of time. This is from, November to something like July in this simulation, driven entirely by pulsating aurora. Now, these are only in local areas on the Earth, right? It's not global, but we are able to see ozone effects and neutral atmosphere effects that last for a long, long time due to the deposition of energy that comes along with pulsating aurora. So very, very cool stuff that we're just starting to understand right now. And this is a little bit how this works. When you have energetic particle precipitation or EPP coming into the atmosphere, you can have this sort of higher altitude deposition, or you can get it down to lower altitudes. If you deposit energy high enough, the polar vortex can sometimes come in and take those constituents lower into the atmosphere where the ozone lives, and that's how you get that ozone loss. Just to give you a little cartoon of how this works, if your electron is low energy, it can create this chemical constituent we call NOx up in the thermosphere, and then maybe the polar vortex pulls it down to the stratosphere, maybe. If your electron is high energy, big blue E, then you can deposit your energy all the way down into the stratosphere directly and create your chemical NOx down there where the ozone lives. But either way, you're going to be able to destroy that ozone in local areas, at least, where your precipitation has taken place. So this is a connection we're still exploring. Yeah, question. I'm pretty much done. Okay, do we have pulsating aurora over the South Atlantic anomaly? No, just primarily because if you trace the magnetic field from the South Atlantic anomaly out into the magnetosphere, it doesn't go out into the outer part of our magnetosphere where chorus waves are produced. So that it's very low latitude and then close to Earth. Makes sense, yeah. Okay, so calculating quantities, I just got the 5-minute sign. So I can do this in 5 minutes. We're gonna talk about this more later in the afternoon in our activity. So I'm just gonna go through this, fairly quickly right now. We'll come back to it. But the idea with our solid state detector instruments, I think you all have been introduced to these, right? As a concept. Okay. So basically it's particles hitting something like activated silicon, leaving energy behind, and then from there we try and figure out what the incident particle looks like that hit that detector or that stack of detectors. But the name of the game for these solid state instruments is these are the ones I build and I work with. How do we get from the count rate, so every time a particle hits you get a count rate of a certain energy, to a particle flux, right? That's sort of the hard part, right? We want to know flux, right? We want to know total particle flux that's happening out in our space environment, but we want to get from that count rate to that particle flux. So we're going to use this relationship here, where R is our count rate. This omega is what we call our geometric factor, which has to do with how the telescope, your solid state telescope, is built, right? How big is the detector? How big is your field of view? That gives you this sort of geometry factor. How big of a sky are you looking at any given point in time? There's our flux. That's what we kind of want to end up with in the end. That's what we want to know, right? Because that's how we make our nice pretty plots with the flux changes. There's our energy and our spectrum. In this case, it's a power law relationship, but it doesn't have to be. And our efficiency term is in there. Okay, efficiency is basically how much of our counts are we actually getting? And that's the hard part there, is there's a certain amount of particles in space, but we're only detecting a certain fraction of them. What fraction are we able to detect? And therefore, can we extrapolate out to what the real flux is? All right, so that tricky part is getting that efficiency for our instrument. And the way that we do that, and also the way that we label our energy channel, right? The way that we understand exactly what energy we're looking at is by using what we call a bow tie analysis. And I'm going to give you some examples using the REPT instrument on the Van Allen probes. This is the one that I've worked on. And I'll show you what those bow tie analyses look like. But the whole idea here is to basically start with this count rate, come up with some we know the geometric factor, come up with some energy and some efficiency, and from there we get back the flux. And that's what we give out to the science community so that people can take the flux and do whatever they do with it and try and understand the physics behind it. Okay, so there's one method of doing this. There's two methods of doing this. So the first one is the method that was propagated by Van Allen and Baker. And you can go look at the paper on this if you want to. But it's basically taking that same relationship I just talked about, but you're going to end up with this quantity of your average efficiency here. And you're going to want to integrate over distinct energy channels, like say from E1 to E2. And then you're going to recover your flux that way with some kind of assumption about the energy spectrum here. So digging into this a little bit more, how do we get this efficiency? We can just rearrange this a little bit and get to an equation like so here. So using this left-hand side and this right-hand side and just solving for that efficiency term. And how do we find this eta term is the hard part. So the way that we do this is we're going to keep E1 sort of fixed to some nominal value that we have already figured out in the lab is probably close to the initial energy that our detector is going to be able to see. So we're going to keep E1 fixed, and we're going to integrate up to different values of E2, and we're going to obtain a curve for each one. And for each of those curves, we're going to see efficiency versus energy. And we're also going to use different energy spectrums, right? So we're going to basically vary gamma within these curves so that we can get different energy spectrums associated with these different curves. Where those curves are all going to cross, the point where they cross is what gives us our energy 2 value and our efficiency value. So I'm just going to give you an example of that. So this is what the bow tie plot for one of our energy channels on the REPT instrument looks like. This is the really high energy 6.2 to 7.7 MeV. And what you're looking at is a way to essentially get the effective efficiency over here on the y-axis and the energy at which point we say that's the high end of our energy channel. And that's where all these curves cross. And that's why it's called a bow tie, because if you were to zoom in on where all those curves cross, you get a bunch of intersecting lines that sort of form a bow tie shape overall. Okay, so that's how we get our efficiency using that method. There's one other method, Selesnik-Blake method, which just does it a little bit differently. And in this method, you're going to actually plot this right-hand side of the equation here versus E bar, I should say, for various values of gamma. And we're going to, again, get a bunch of curves, but we're going to get delta E or the spread of the energy, the width of the energy channel versus E for various energy spectrums. So that curve looks like this for the same energy channel. And we again get a bunch of curves, and where they intersect is where we're going to be able to determine our delta E or our bin width of our energy channel, and then our E or our characteristic energy down below. Okay, so two different ways of getting similar quantities that basically define your energy channel and how efficient that energy channel is. And this is just a table of, you can do this with a bunch of different exponential versus power law. You can do this with a range of, you know, your gammas or your E naughts, depending on what you think your distribution in space looks like. You do that with a bunch of different parameters, and you end up with a table here, and then you basically have to decide which one you're going to use. So you have to report something. So you have to either use, you know, method 1 or method 2, and you have to either use an exponential or power law. And you can see you get slightly different energies and energy ranges based on which method you use. Later, we're going to talk about how we decided which method that we used in the end. That's for the afternoon. So that's it.
So what we're going to do is, I know there's a lot of questions, but we're going to take a 5-minute restroom break, water break, come back at 25 after. So write down your questions, and we're going to have questions for Stuart and Allison. We're going to have this open discussion Q&A. And we've also got a introduction to the afternoon activity, but then we're going to break for lunch. And then you can continue conversation over lunch, but just a quick 5-minute break and then we'll be back. So, thank you. Okay, everyone, we're gonna get back for about 35 minutes of some discussion. And hopefully you can start seeing the theme of the summer school, looking at observations and quantities. When you think about getting a flux here, she also had plots of the intensity as a function of mu, k, and L star. So how do you make those and what do they physically mean? And when you think about energization, you need an energy source somewhere. So what does a distribution function look like in terms of T perp and T parallel? And why does plasmaspheric density have an impact on EMIC wave growth or whatever? All these things are interconnected and you're usually making measurements at a single place. But wanted to open it up for any questions. And we'll start if there's one or those for Allison, and there were a couple of hands up. So, well, you can have start.
So I have two questions. It's related to two slides. So you showed a very first slide with the like the Van Allen radiation belts from 2012 to 2019. I know it's like not a complete solar cycle, but does it have any relation to that? Anything to the solar cycle? And then you also showed a plot with the histogram, basically the, the geomagnetic storms and like the fluxes. Does it have any relation to each other?
Yeah, okay, good question. So this one here, it does have a relation to solar cycle. So in 2015, we started in this declining phase of the solar cycle. And that's when you often see, actually Stuart probably know this better or know why this is true better, but in the declining phase, you'll see a lot more of these high-speed streams or these CIRs rather than CMEs. And so we can see that in this plot here, right, with our repeated accelerations that come over and over again. Prior to that, we had a lot of, and then down in here, we had a lot of CME. So here we're starting to pick back up in solar cycle. We had a lot of CMEs, but they're just not as efficient at accelerating particles. So you just see these sporadic accelerations, right, rather than the constant, like all the way through 2016 and end of 2015. There's just this like constant several times per month or a couple of times per month, you get accelerations like over and over and over again. And that's just long-standing coronal holes that are just sitting there, rotating across the sun and hitting towards Earth over and over again as the sun rotates. So we can see the solar cycle, I think, pretty clearly here. The CME period, when you were in 2013 to 2014, it was a weak solar maximum, right? So we didn't get a lot of the CMEs we maybe would have if it were a strong solar maximum. But other than that, it does look very much solar cycle related to me. And then your other question about the storms. Yes, there's been a lot of work trying to relate geomagnetic storms to solar cycle, and then solar driver is really the big one, right? So it's not even really just solar cycle. Solar cycle tells you you're more likely to have a CIR versus CME, but you can have a CME in a declining phase, right? So it's just what's more likely. And what we see with the storms is that it's not even just the solar wind transients that are at play with how the storm affects Earth, but the substructure of the solar wind transients. So when you have, like you have a CME, with a shock, that can be more geo-effective or more, we see more radiation belt effects than if you just have a CME. So it's like the substructure within the solar wind transient that we are now understanding is more important than solar cycle or even just the big scale transient label.
Yeah, so kind of also two questions about the 2015 storm, which you have a figure for the 4.2 MeV electrons. So like, in the figure, it looks like the increase in the density is like a few days after the storm impacts.
This one?
Yeah, that one,
Okay.
right? It looks like, or like a day or
Yeah.
so. And like, is there any like reason for that? And then my second question, which is a bad question, is this a typical sort of thing?
Okay. You know the answer to that, because if you've seen one storm, you've seen one storm. This one, so this is the bottom right-hand plot is an example of this inward radial diffusion, where it's a diffusive process and it's really rather quite slow. So at this energy, which is 6.3 MeV, highly ultra relativistic, we didn't see that energization happen until things diffused inward from lower energies to get up to those higher energies. So yeah, there's a delay. And it's kind of nice if I were to show multi-panel of different energies, you would see like the 7 MeV happen later and the 8 MeV happen later and the 5 MeV happen before this, right? Because you could see the energy take place as the diffusion happened, which happened over a matter of hours to days. Question though.
I had questions about the solar cycle dependence, that plot that you
Yeah.
were showing before. Because you said you can identify CMEs and then HSS as well, the high-speed solar stream. So, so how do you distinguish between those two phenomena in these plots? Because
Oh.
I'm not really aware.
Yeah,
Is it a threshold in energy?
you can't, you can't really distinguish in these plots. What was the solar wind transient that hit Earth? You can't really distinguish just from looking at these plots. I'm making a generalization in that we had a lot of HSSs and you can kind of see that with the repeated acceleration over and over again. But to really understand what's impacting the magnetosphere, you have to go to the solar wind data itself and look at like, what does the magnetic cloud look like, right? And look at all those solar wind parameters, the B field and the speed and how it changes over time. And all those give you clues as to like, if you're looking at a shock, a CME, and HSS.
And how the southward magnetic field is impacting or not.
Exactly. Are we looking at southward BZ? How sustained is the southward BZ, or does it flip back and forth between northward and southward? Those all give us clues as to what the actual transient is. But this, you can't tell.
We're still at the level of one storm is one.
Yes. Yeah.
Yeah, and there's a lot catalogs that most of the instrument teams and experiments have, a catalogs of all the magnetic clouds or the CMEs or the shocks. And so those are often useful resources if you want to try to look at what drove your event, is see if anybody's identified.
Yeah.
You have a question here and then over there.
Thank you. Can you go to the slide showing the triangular distribution of the electron flux? Like for me, like I'm seeing that higher velocity triggers higher flux, but also, as you mentioned, like lower velocity in the solar wind triggers both higher and lower. I'm so sorry because I got anxious. But why does this happen? Like the slow solar wind triggers both?
Yes. So this was kind of my point in that storms, or what sometimes you can define a storm by the solar wind speed, right? So high solar wind speed, you can define thresholds for what gives you a geomagnetic storm. And storms are not what ultimately defines the flux of the radiation belts. So that was my point here. It's something else. Right? It's not storms, because if it was, then this would not look like a triangular shape. It would look more linear. You would have low flux at low solar wind speeds, and it would go up to high flux at high solar wind speed. But this characteristic triangle, which we've seen over and over again in a bunch of different, not even just solar wind speed, a bunch of different solar wind parameters, that means that there's something else happening that, yes, you'll always get a big flux at high solar wind speed, but you may also get big flux at low solar wind speed. And that's because of substorms, which are these smaller releases of energy in the magnetic tail that happen every day. And they can happen during low solar wind speed, non-storm time, also during storm time. But that's really what we think is critical for building up the radiation belts, and not the big storms. Although it does happen during the big storms, but it's not it's not a necessary prerequisite.
Thanks. You just answered one of the questions I wanted to ask. But the second question I would like to ask is, this radiation belt that are released, you said it affect the stratospheric polar vortex.
Yeah.
Do they then affect the local atmosphere?
Yes. So it's a little bit, wrapped up in energy spectrum. So I'm not showing you how the energy relates to the altitude deposition, but the radiation belt or ultra relativistic, MEV energies, they have enough energy to deposit all the way deep into the stratosphere. So they would be like the big E, the big blue E. And they would have enough energy to get all the way down to the stratosphere directly. If we're going a little bit lower in energy, they might only get, into the bottom of the thermosphere. And if we're getting to, lower energies in the hundreds of keV, you're only getting into the thermosphere, and you have to get transported down. The polar vortex can mix things around, and it can pull things from higher altitudes to lower altitudes. And so that's how you can get some of that circulating. But yeah, this is really an effect that happens from radiation belt electrons all the way to the top of auroral energy electrons.
Hi, I have two questions. Like during the talk, you told that in case of bounce motion, V perpendicular and V parallel play role. But what about gradient in magnetic field?
What about gradients in magnetic field?
Yeah, in case of bounce motion, gradient in magnetic field plays a role, right?
Yes.
So
yes.
is there any evidence that for when the gradient is much higher, like in case of polar region, generally it is the case. So what happens when for closed magnetic loops?
What happens?
When the gradient of magnetic field is high, then parallel and perpendicular component of velocity, how do they play a role? With respect to gradient. Right?
Yeah, so I think what you're getting at is where does the actual mirror point happen?
Yes.
So where does that particle turn around in its bounce motion and maybe go back out in towards the equator and then go towards the southern hemisphere and so on?
Yeah.
Yeah. So that depends on what the component is of its parallel velocity to begin with, right? And so that's where that mirror point. That's what determines that mirror point. Also the gradient, right? So as you get into your asymmetric Earth's magnetic field and you have things like the South Atlantic anomaly and the corresponding magnetic footprint of the South Atlantic anomaly, you get changes in precipitation that we can see with data because we have an asymmetric field. It's not a perfect dipole around Earth, even close in, right? We have these asymmetries in there. So in the SAA, we get a lot of precipitation that we see because the mirror point is lower there in that region. And so things that would normally mirror and go back out into the magnetosphere are just going to hit the atmosphere in that region.
Okay.
Yeah, does that answer your question?
Yes, it depends on gradient. That is my point.
Yes,
and
it
you have
depends on
explained
yes,
that.
exactly.
Second is that when you quantities, like measurable quantities, in case of energetic particles, generally count is particle count is the primary quantity and flux is derived quantity. Now you have shown we are calculating count from flux and some energy spectrum. So isn't it the case opposite, just opposite?
Opposite. Okay, so I think you're asking, are we making assumptions?
Yes.
And we are. Because that's all we do as experimentalists, right? We make assumptions and then we give our best guess at what we've measured, versus the ground truth. That's the best we can do. So yes, we assume some energy spectrum, and then from there we can back out the flux. But we have to start with an assumption of an energy spectrum, and we've measured it. We've measured energy spectrums before in space plasmas, and we kind of have a handle on how we think that works. But we always see inconsistencies from that. So sometimes our measurements might be wrong because we're using an assumed energy spectrum, and at that point in time, we don't have that same energy spectrum in our overall plasma. So we might end up reporting the wrong value.
Also, we are just taking two kinds of power distribution. Like one is power law, another is exponential.
Yes.
So if the energy spectra is different than these two, then what will happen?
Yeah, exactly. That's what I mean. We have pathological spectra sometimes that don't follow a power law, don't follow an exponential directly. And in that case, our reported values are going to just be a little bit wrong. We can't do anything about that because, like you said, it's a circular process. To measure the energy spectrum, you have to assume an energy spectrum. And so don't trust the data and don't ever trust the data entirely because we're always making assumptions.
Hi, I want to go back to the dropout events
Oh yeah.
and just like think about that for a minute. Said magnetopause is often compressed.
Yeah, during a dropout events, we often like see a compression in the magnetopause, but it's not going to compress all the way down to where we see the dropout occur and deep into the magnetosphere.
Yeah. Do you know like what parameters have been ruled out for causing these? I don't know. This is like a hard question, right?
Yeah.
Up in your head, but
Yeah, well, no, I mean, we don't know. This is sort of the open question. Like, is it wave particle interactions that are doing this precipitation suddenly across lots of L shells and lots of energies, which is a little hard to believe? Or is it magnetopause compression together with enhanced outward radial diffusion? So you're kind of like draining the particles out to the boundary.
okay.
And the boundary has moved closer in, so it's easier to drain them out towards the boundary.
Right. And then are
sort of-
these,
sorry, sort of in this, no, this process here where like you've cut off, you know, your magnetopauses come in and you've cut off half your distribution already. And then it's really easy to drain particles out that outer boundary.
okay. And then are these like during storm events?
Yeah.
Definitely. And then is it specific storm events like, you know, with IMF in a specific direction or something like that?
That's a good question. Someone should look at that.
Okay.
I don't know.
Yeah, in general, when you think about the nominal location of 10 RE upstream, what in the solar wind drives that earthward? Is usually a solar wind dynamic pressure increase, but there are other processes in terms of getting very local motion. Any other quick questions or what more?
So for the very high energetic particles that get down to the stratosphere, right? Is that what the black aurora is? Is that when people talk about, are they completely separate things?
Completely separate things.
Okay.
Yeah, so black aurora has to do with current closure, we think. Now, again, we don't know a lot about our ionosphere, which is crazy because it's so close to us, but you know, it's hard to measure things there. So we have to either do rockets that get up to 100 kilometers, or we have to do some kind of remote sensing from the ground. You know, we can't fly a satellite at 100 kilometers. It's just too much drag. It'll immediately deorbit. So we could drop off CubeSats and let them deorbit through there, but you know, it's just very hard to measure that region. So we don't really know a lot about what's going on, but we think the black aurora, you often see it in sort of stripes between, you know, discrete or maybe, you know, maybe diffuse aurora. And we think that has to do with some current closure. So you think of a current sheet, right? And where the current sheet is going in the opposite way, you're going to have an absence of precipitation, whereas it's going in the other way, you're going to see the precipitation. But we've seen some really like funny black aurora stuff where it's like little dots in the middle of aurora. And those dots are little, you know, little fish, we call them, like just kind of move around quickly. And we see this like absence of aurora as this little black dot that kind of like moves around. It elongates, it changes shapes, and then it disappears. I'm like, what the heck is that? You know, nobody knows. So there's really strange stuff that still to figure out.
Yeah, so all of the instruments that we've looked at so far and we'll look at again, you can think about the fundamental thing they're measuring, a voltage or a pulse current that you sweep out. We almost always want to have some understanding of the accuracy and the precision of the measurement. And so we try to come up with an uncertainty, an error. I can measure within 10% or 20%. And as you start looking at how you actually derive flux, right? An ideal instrument measures everything you want and nothing you don't. So how do you do that? So how do you take into account background counts, right? You start thinking of what's my error budget? So where is all my sources of error? And it could be intrinsic to the instrument, and you can start thinking about dark currents and thermal effects. How well do you know your geometric factor, or all this efficiency aspect to it? And then you could start thinking about, I need to make an assumption over a distribution to back out this, right? So I'm making a model, and then I could have a sheath for the spacecraft that could be retarding certain particles coming in, or I might be only measuring ions or whatever it is, right? You have all of these uncertainties. And now if I'm trying to look at a pitch angle distribution, I need to know where the magnetic field is. So how do I couple in uncertainties of the magnetic field? And then I want to put it into some coordinate system with reference to what I think my instrument coordinate system is. So now I have to know where my spacecraft is oriented. So how well do I actually know where I am, right? So all of these things start adding up. And often it's not your instrument that's the main cause of error. It's, I don't know where I'm looking, or there is a obstruction in my field of view, and I'm making an assumption when I integrate over a distribution. You know, I'm going to assume it's a Maxwellian, and I'm just going to fit a Maxwellian to it. So all of the instruments, start thinking of that error budget, and you can make your name for yourself as an experimentalist if you can really understand those terms and try to start beating them down. And you can come up with a whole new idea of measuring a parameter, or you can design your experiment or your mission to have multiple ways of measuring the same parameter. So I can have a plasma wave instrument that gives me plasma frequency, that gives me density, that could help me figure out my electrostatic analyzer distribution function or whatever, right? So there's a lot of tricks and why there's a lot of complications. We're going to start talking about multiple instruments like Van Allen probes, and I'm looking at gradients. So I'm going to be looking at a difference between the two how do I know they're intercalibrated? Is it
Yeah,
really?
Let me ask the group, like, what's one way you can try to check if your instrument is measuring the right thing? If you're already, so say you're already in space, right? And you just, what's one way you can try to check? Yeah, say it again.
Compared to spacecraft data, which is like if they're measuring the same physical quantities.
Yes. Yeah, exactly. So you can look at another instrument. Maybe you have a small overlap in energy, and you can try to see if that works. So like, for example, we did that for REPT, we used the other particle instrument on board, which was MagIce, and it had a very small overlap in energy. So at the bottom of the REPT energy range, which is the red blue stuff, and the top of the MagIce energy range, which is the yellow stuff, we overlap just a little bit in energy. And so then we can try and plot the whole energy spectrum and see if we match. What do you think? Is it good or not?
Should you write a paper on saying, oh, there's a little kink there?
What do you,
Must be local.
It looks like somebody is high, or someone else is low, right? So MagIce, the yellow, looks like it's either low or the REPT is too high. Now, which one do you go pick on and say, like, you're wrong? It's either REPT or MagIce is slightly off. How do you figure out which one it is? I mean, that took years of my life. that question.
So some instruments are really nice because you can actually fly a calibration source, so if you're a spectrometer and you could just have a lamp, and so I know what my frequency is, but for the most part, we're flying sort of blind. We're assuming we're doing a really good job of calibration on the ground and that we have a way of doing some calibration in space. I mentioned yesterday for magnetometers with IMF, you can take, Alphane wave is going to be going back and forth. And so I can use that as trying to figure out some offset, right? So you can think of, what is the limit or what do you expect? Any other questions? Yes, Lika, and then up front.
Actually, this is an interesting sort of segue on calibration. I'm not going to use example of in situ data. I'm going to use example of a remote sensing data set where we have done this cross calibration. And I'm beginning to wonder, we have just done one experiment on a very large data. I'll tell you what it is. But maybe we should be thinking about starting those kind of experiments with our in situ data calibration in space. So what we did in 2018, a small group came together, domain experts, computer science experts, Google, NVIDIA, experts in algorithm development. And over a period of 8 weeks, we asked the question. So many of you are familiar with solar dynamics observatory data. It's the largest data volume we have in heliophysics. And one of the critical instruments that provide direct energy input into ionosphere, MEGS-A, it's the Eve instrument, which has 3 sensors, and the MEGS-A component of it malfunctioned in 2014. So SDO launched in 2010, MEGS-A malfunctioned in 2014. So we do not get direct measurement of that spectral range that is critical for energy input for ionosphere. So in 2018, and NSDO has many other data sources, atmospheric imaging assembly with 10 filters taking data in extreme ultraviolet. We have HMI, helioseismic magnetic imager, taking magnetic field data. And then we have the 2 other components, MEGS-B and the other one for Eve. So the question that was asked, can we take all the data that we have collected from 2010 to 2018 by various instruments on SDO, use those data to train MEGS-A kind of data and get that verified and validated for as long as we were taking data up to 2014? And then can we actually predict MEGS-A result? Well, we not only were able to do that, just this year, we are finishing up a much bigger volume data for SDO. We had used limited amount of data. In 2018, we can see that we can actually calibrate in space. So right now, SDO has a rocket under flight to do the calibration for Eve data, Eve instrument. In future, when we fly instruments, we can begin to take these kind of cross-calibration approaches because we will fly many instruments. And the reason I'm sharing this is that there might be such possibilities with the in situ data because we are always collecting a variety of data, which has inherent stored information that we haven't really pulled out yet. Thank you.
Yeah, so there are missions that actually depend on rocket flights every year to fly to help calibrate the data, right? So there's different ways of thinking, I can't fly it with me, but is there another way? And so Stuart, what's the biggest Parker Solar Probe challenge of going in close to the sun for any of the particle data or electric field? You have a mic yet?
I think I'd say probably it's the same thing. It's the calibration of the thermal plasma instruments, which have limited fields of view. we have this big heat shield on the front of the spacecraft. And so they have to look around the heat shield. And for the electrons, it's maybe not quite so bad, but for the ion instrument, the wind has to be, if the wind's too fast, it's too radial and the beam is cut off. And so the beam drops out, density drops out. And so we've mitigated that with, as you alluded to, Mark, plasma wave instrument that measures what's called the quasi-thermal noise spectrum. So it measures the ambient spectrum of fluctuations, thermal fluctuations of electrons as they excite currents on the antenna. And that occurs in an eigenmode, in the Langmuir wave eigenmode. And so it occurs at a resonance, at the plasma frequency resonance. And so it gives us a distinct spectral feature that tells us the plasma frequency to really whatever accuracy you want to digitize it to. It's accurate to the stability of your clock, which can be very, very accurate, 100 parts per million or something, and to the spectral resolution of the instrument. So we have 1% spectral resolution, and so we can get a pretty good density measurement on that. I think it's, it works when the density is high enough. When the density is low and we're far from the sun, it doesn't work. But it's kind of saved us on a lot of the plasma physics on Solar Probe, I think.
Yeah, that's the other, when you're looking at a data set and the parameter, want to calculate how far removed are you from the actual physical parameter. Sort of the gold standard of a measurement is something that's due to some fundamental plasma frequency or cyclotron frequency, something that is just proportional to constants, Q and M, but how far away, what type of assumptions and modeling and curve fittings and conversions you have to do. And so that gives you a better sense on error bars. So when you're comparing wind and discover, and they're different, they could be because they're actually measuring different solar wind parcels, but it could be they're in a regime that the response of the Faraday cup is different than the response of the electrostatic analyzer. And so understanding what those ranges are and where the uncertainties become bigger under what conditions can help you solve it.
Just to follow up on that, do you use the electron densities and assume quasi-neutrality to get that ion density?
Yeah, we generally assume quasi-neutrality. We're measuring the electron density, essentially the total electron density, right? And there'll be a core, a straw, a halo component. There's separate components. But yeah, then you have, of course, you have a measurement of the ion density is dominated by the protons and to a few percent alpha particles. And so you have independent measurements of those. And you can really see when the proton or when the ion instrument is failing because the beam just goes out of the field of view and it's kind of choppy and drops out. And so it provides kind of continuity on that. And to go back to the idea of measuring a frequency, a power spectrum is a function of frequency. A good thing about it is that it doesn't depend on the absolute calibration, right? You're looking for a spectral feature, essentially. There's a famous quote from Charlie Towns, the inventor of the laser, who said you should never measure anything but time, because you can measure time very, very accurately, right? So if you can convert your measurement, whatever it is, into a measurement of time, you've got really good, accurate measurements.
Plot that Allison's got up there. So not only do you have these problems of who's right and who's wrong, right? So there's a like, you want them, in theory, they should be giving you the same answer, right? They overlap. And, but the question is if they're not, one's high, one's low, maybe they're both, high and low, and the answer is really in the middle. But one of the difficulties often with this kind of thing is that we typically build, so I'm going to say energetic particle instruments, right? You can't measure the whole distribution usually with one particle instrument. It's just too hard. There's too much of a range in energies. And so, and you do want to have them overlap so you can intercalibrate, but you don't want to have them overlap a huge amount because then you're just sort of, you're not maximizing the amount that you can look at because you have finite resources and stuff. The problem is that where they overlap is typically, as Allison said, at the high end of one detector instrument and at the low end of another instrument. And generally the high end and the low end are where the instruments don't behave the best. So usually the low end is where, or at the high end is where you're losing efficiency for whatever reason, right? And so you're now intercomparing two parts of the instruments where they're not really doing their best job. And so that makes it additionally hard, which is probably why Allison spent a couple of years of her life trying to figure this out, because now you really got to understand all the efficiencies and all the weird stuff that happens sort of around the edges of your instruments, that where if you were just looking at one instrument, you'd probably throw out those data points. A lot of times what we do is we say, well, the lowest energy bin and the highest energy bin, we don't even really plot those because things start to get wonky around there. Well, if those are the only places where you have overlap, you can't ignore them. So then you've got to worry about, you know, all these extra little effects. So it can get a little challenging.
Yeah, and then we're trained in different schools of thought in terms of plasma parameters or MHD, large scale, give me temperature, density, and velocity, and others are actually counting individual particles. So I want to know my distribution function. And so I want to know about the straw and the superthermals, and I want to know T parallel with, is there a bump on my tail? And so there's a lot of different data sets that come out that from a single spacecraft, and trying to, how do I actually organize this to actually, how do I know there are EMIC waves and ULF waves? Well, I need that magnetometer. Well, how do I know where they are? I'm a single point measurement, and things drift. So when I see it local, it doesn't mean that whatever happened there. It could have happened elsewhere and just came to me. So detangling this propagation effect of energy or particle distributions is a big game, and why we are going to multiple point measurements. And so as we go through tomorrow and the next day, we're going to be talking about MMS, trying to figure out how do we measure gradients and how do we detangle this time and space, local versus transport and propagation effects. So we are, I can't remember, what time do we go for lunch? Okay, perfect. And last few questions. Yep.
Hi, I have a question for you, Stuart. You mentioned earlier that there's some difficulties taking electric field measurements on the Parker Solar Probe. Maybe I'm wondering what the challenges you face are.
The main challenge is that the probes, the voltage probes, are too short, right? So what you really want to make a good electric field measurement is, you're trying to measure the local plasma contact voltage, and so there's some tricks you can do, like biasing your probe to bring it closer to the sweet spot on the Langmuir probe curve, et cetera. But you really want to be far from the influence of the spacecraft. So the spacecraft has a Debye sphere around it. And so on probe, we have 2 meter long, well, 2.3 meter long antennas. And we actually originally proposed with 1 meter, and we got a silver bullet from APL, and they let us extend them to 2, a little bit more than 2 meters. But that's still, the Debye length, the spacecraft Debye length gets down sometimes to maybe 30 or 40 centimeters at perihelion, where it's really dense. And that's when we can do our best measurement. The probes are also not, they're designed to be kind of a hybrid, so we can do this quasi-thermal noise measurement, this measurement of the plasma frequency, and try to make a DC electric field measurement. In a perfect world for a DC electric field measurement, you'd have your sensor be a sphere, because a sphere kind of always projects the same area to the sun, independent of its orientation. But we compromised to get this plasma calibration line too. So it's a compromise instrument. It's a simple thing. Works some of the time when the plasma is very dense, when the V cross B is, when the velocity and the magnetic field are big, basically, so we can do a good calibration of it.
The electric field probes are never long enough
No, they never.
on
Well,
any mission.
yeah, that's kind of right.
Never
That's how
work.
people feel about it.
Well, and then there's shadow periods sometimes, which drastically changes the response of of your spheres. If you're in a planetary environment, there's oxidation. So if you go too low close to the planet over and over again, over time, the sphere material oxidizes, and that changes the electric field response.
Surface properties change, and so the
Yeah.
photoelectron flux changes, and yeah, it's a hard measurement.
I have a question based off of what Stuart said. You said we are really good at measuring times. Are we good at measuring quantities simultaneously? How good are we with simultaneous measurements? You said it's good to have, let's say, 20 measurements a minute.
Yeah.
But are we good at taking those measurements exactly at the same time, or there's definitely wiggle room, but do we
Well,
not
this kind
share?
of goes to the clock, okay, so for a given instrument, yes. So if you have one instrument, you have a clock, you can put a crystal control on it and have, 10 parts per million accuracy on the clock itself. What you really want to do, of course, is have, if you're combining, like on Solar Probe, where we're combining magnetic field measurements with plasma measurements, we want to have those be essentially synchronized. And so that's what we've done on Solar Probe. We have a wire that goes between the two instruments, and we pass one of the instruments, the field's instrument, my instrument passes a clock to the other one. And so we chime on the same bells on the clock. If that wire is broken or if one of the instruments is off, then we go independently, and we can see that. Actually, there have been a few times when we've turned off the wire and we can see the measurements drift apart. And worse than that, we can see when they drift apart, the clocks, the instruments which are nearby to each other beat against one another. Those two clocks beat against one another, and we get sum and difference signals, and we can see those in the measurements too. We can see the difference between the two clocks, which is a very low frequency. The clocks run at 38 megahertz or something like that. It's a very low frequency, and we can actually see that modulation in the measurements too. So having synchronization to the best you can, having crystal control, all those things makes for really clean measurements.
And when you look at modern electronics, there are something milliseconds, microseconds, nanoseconds, and you can have RC time constants and picoseconds, right, for trying to sweep out a high flux account. So you need really precise timing, and then interspacecraft timing, particularly for things that are not within GPS, becomes a big challenge. But so navigation, position, and timing.
It's all technically possible. It just has to be built in. You just have to think about it when you're designing things.
Okay, last question.
You said earlier that if we are to develop our results working with time series, it does not necessarily bring out the features or the right results that we are looking forward to. So you said we should convert our results to coordinate-based systems where we see the features of the result. My question is, how do we know which appropriate coordinate system to use?
Well, that's a good question. That's a good question. I mean, and of course, it's not always the thing to do, but when it can be done, when you suspect you're looking at something that's, for example, that's time stationary in some coordinate system, but you're flying through it with a spacecraft and all you have is a time series, you often learn a lot by trying to convert it back into some time stationary coordinate system, some inertial coordinate system, or some, sensible coordinate system. I mean, again, you're building in an assumption when you do that, of course, and you can try to test that assumption and prove it wrong. So there's always the risk that you're building in something of confirmation bias, that you're looking for something and finding it when it's not there. But in a lot of cases, it's just sensible. I think you learn from the time series measurements what's going on, and then you try some different coordinate system transformations, and suddenly something seems really physical.
Great. Please thank both of our speakers this morning, and they'll both be around this afternoon. So if you've got more questions for them or want to interact more or quiz them about their various failures that they've experienced, feel free to do so. I have 3 instructions for you. Instruction 1, go to lunch. Instruction 2, be back here by 1, because Lika would like to talk to you, give you a little bit of overview of some of the things that she's thinking about, and also interact with you too. And then instruction 3, those of you who have posters next door, as part of the participant talks, what I'm going to have you do is give you stand up, you'll give your name, the title of your poster, and a 1-sentence introduction to your poster. And the 1 sentence can include exactly 1 conjunction. And if you don't know what a conjunction is, look it up. So, so we've got, I counted 11, but they're supposed to